55 Cancri E is a diamond planet. Deep within the vast expanse of our galaxy lies 55 Cancri E, a planet unlike any other in our solar system. It has earned the intriguing nickname Diamond Planet due to scientific estimations that suggest it is primarily composed of crystallized carbon, specifically diamond. This celestial body orbits the star 55 Cancri, a sun-like star located approximately 40 light-years away in the constellation Cancer. What makes 55 Cancri E stand out from the myriad of other exoplanets discovered so far is its unique composition and extreme environment. The story of 55 Cancri E begins with the discovery of its parent star, 55 Cancri, which was already known to host a planetary system with multiple planets. The discovery of 55 Cancri E added another layer of intrigue to this already fascinating system. The planet is categorized as a super-Earth, meaning it is significantly larger than our own planet but smaller than gas giants like Neptune or Uranus. Its mass is estimated to be around 8 times that of Earth, and its radius is approximately twice as large. What truly sets 55 Cancri E apart is its incredible density. Scientists believe that the high density, combined with the star's carbon-rich environment, suggests a predominantly carbon composition. Under immense pressure and heat, carbon atoms can bond together to form a crystalline structure, diamond. The environment on 55 Cancri E is far from hospitable. It orbits its star at an incredibly close proximity, completing one orbit in a mere 18 hours. This extremely tight orbit results in scorching temperatures on the planet's surface. Estimates suggest surface temperatures could reach up to 3,900 degrees Fahrenheit, far too hot for liquid water or any life as we know it to exist. The intense heat and pressure within the planet are also key factors contributing to the formation of the diamond structure. The high pressure compresses the carbon atoms, while the heat provides the energy needed for them to bond in the strong, crystalline lattice characteristic of diamond. The possibility of a diamond planet raises fascinating questions about planetary formation and the diversity of planetary systems in the universe. While Earth is a silicate-based planet with a relatively small amount of carbon, other planets like 55 Cancri E might form under different conditions where carbon is more abundant. This could lead to the creation of exotic worlds with unique geological properties. The discovery of 55 Cancri E challenges our conventional understanding of what planets can be made of and inspires us to look beyond our solar system for other unusual celestial objects. It is important to note that the diamond composition of 55 Cancri E is still a theoretical estimation based on available data. Directly observing the planet's interior is impossible with current technology. However, continued observations and advancements in astronomical techniques could provide more definitive evidence about its composition in the future. 55 Cancri E is a testament to the boundless possibilities that await us as we explore the cosmos. It is a reminder that the universe is filled with wonders beyond our wildest imaginations, and it inspires us to continue pushing the boundaries of scientific discovery. A day on Mars lasts 24.6 hours. Alright, let's delve into a fascinating comparison. Earth days and Martian days. We all know that a day on Earth clocks in at roughly 24 hours. It's a rhythm we're intimately familiar with, dictating our sleep cycles, work schedules, and the ebb and flow of daily life. But what happens when we venture beyond our blue planet and set our sights on the rusty landscapes of Mars? Prepare to adjust your cosmic clock, because a day on Mars, more formally known as a sol, isn't quite the same. A sol on Mars lasts approximately 24.6 hours. That extra 36 minutes might seem insignificant, but it's a subtle difference that has intrigued scientists and space enthusiasts alike. Imagine living on Mars. Your days would gradually shift relative to Earth time. You might start your Martian day at the equivalent of 8 a.m. on Earth, but over a few weeks, that starting point would drift later and later. This difference presents unique challenges for planning and coordinating missions to Mars. Mission control teams on Earth have to synchronize their schedules with the Martian day to effectively communicate with rovers and astronauts exploring the surface. They essentially live on Mars time, adjusting their work hours to match the Martian sol, even if it means some very unusual sleep patterns. This slight difference in day length is due to Mars's rotation rate. Planets spin on their axes, and the time it takes for a planet to complete one rotation determines the length of its day. While Mars and Earth are similar in many ways, including having axial tilts that cause seasons, Mars rotates just a tad slower than Earth. This seemingly small difference adds up, giving Mars that extra half hour each day. The implications of this 36-minute difference aren't merely academic. Consider the psychological impact on future Martian colonists. Adapting to a different day length could affect sleep patterns, mood, and overall well-being. Scientists are actively studying the effects of living on Mars time to better prepare for long-duration missions and potential human settlements. Furthermore, the length of a Martian sol plays a vital role in understanding Mars's climate and weather patterns. These additional minutes contribute to variations in temperature, wind speeds, and atmospheric pressure. They influence the behavior of dust storms that can engulf the entire planet. Studying the intricacies of the Martian sol allows scientists to build more accurate models of Mars's climate, helping them predict weather events and understand the planet's overall environment. The fact that a day on Mars is just a bit longer than a day on Earth highlights the delicate balance of factors that shape a planet's characteristics. It reminds us that even small differences in rotation can have significant consequences for a planet's climate, environment, and ultimately, its habitability. So next time you think about the length of a day, remember that on Mars, time marches to a slightly different beat, adding another layer of intrigue to the red planet. A solar eclipse happens when the moon blocks the sun. A solar eclipse is one of the most breathtaking celestial events we can witness from Earth, a cosmic ballet where the moon momentarily obscures our star, the sun. This awe-inspiring phenomenon occurs when the moon passes directly between the sun and the Earth, casting a shadow upon our planet. The alignment must be precise, a straight-line configuration known in astronomical terms as syzygy. But it's not just any alignment. The moon's orbit is tilted relative to Earth's orbit around the sun, so these perfect lineups are relatively rare. The shadow cast by the moon during a solar eclipse isn't uniform. It consists of two parts, the umbra, the darkest, central part of the shadow, and the penumbra, a lighter outer region. If you're standing within the umbra's path, you'll experience a total solar eclipse, where the sun is completely blocked by the moon. The sky darkens dramatically, stars may become visible, and the temperature can drop noticeably. It's a surreal experience that has captivated humanity for millennia, inspiring myths, legends, and scientific inquiry. Observers within the penumbra, on the other hand, will see a partial solar eclipse, where only a portion of the sun is obscured. The type of solar eclipse you see also depends on the moon's distance from Earth. The moon's orbit is not perfectly circular, so its distance varies. When the moon is closer to Earth, it appears larger in the sky, and a total solar eclipse is possible. However, when the moon is farther away, it appears smaller, and even when perfectly aligned, it cannot completely cover the sun. This results in an annular solar eclipse, where a bright ring of sunlight remains visible around the moon's silhouette. This ring of fire, as it's often called, is a spectacular sight in its own right. The path of totality, the narrow strip on Earth where a total solar eclipse can be seen, is quite small, often only a few hundred kilometers wide. This means that total solar eclipses are only visible from a limited geographic area. The duration of totality is also limited, rarely exceeding a few minutes. The longest possible total solar eclipse can last just over 7 minutes, but most are significantly shorter. It's important to remember that looking directly at the sun during a solar eclipse, even a partial one, is extremely dangerous and can cause serious eye damage. The only safe way to view a solar eclipse is through special-purpose solar filters, such as eclipse glasses, or by using indirect viewing methods like pinhole projection. These filters block out the harmful ultraviolet and infrared radiation, allowing you to observe the eclipse safely. Solar eclipses provide valuable opportunities for scientific research. During a total solar eclipse, when the sun's bright disk is blocked, scientists can study the sun's corona its outermost atmosphere, which is normally invisible due to the sun's intense glare. These observations can help us understand the sun's magnetic field, solar flares, and other phenomena that affect Earth. The study of solar eclipses has significantly contributed to our understanding of the sun and its influence on our planet. They also allow us to test Einstein's theory of general relativity, as the sun's gravity bends light from distant stars, which becomes more visible during an eclipse. In short, a solar eclipse is far more than just a pretty sight. It's a chance to unlock some of the universe's secrets. Alpha Centauri is the closest star system to Earth. Alpha Centauri, a celestial neighbor often whispered about in astronomy circles and science fiction alike, holds the distinguished title of the closest star system to our own. Located a mere 4.37 light-years away in the southern constellation of Centaurus, this proximity makes it a subject of intense scientific curiosity and hopeful speculation regarding potential extraterrestrial life. Instead of being a single star like our Sun, Alpha Centauri is a triple star system, composed of 3 stars gravitationally bound together. The 2 primary stars, Alpha Centauri A and Alpha Centauri B, are Sun-like stars, with Alpha Centauri A being almost identical to our Sun in terms of size, mass, and temperature. Alpha Centauri B, while still a main sequence star, is slightly smaller and cooler than its counterpart. These 2 stars orbit each other in a relatively close elliptical orbit, completing 1 revolution approximately every 80 years. Adding to the complexity and intrigue of this system is Proxima Centauri, a red dwarf star significantly smaller and dimmer than the other 2. While its exact orbital relationship with Alpha Centauri A and B is still debated, it's widely accepted that Proxima Centauri is gravitationally bound to the system, making it the 3rd star in the Alpha Centauri family. The discovery of Proxima Centauri b, an Earth-sized exoplanet orbiting within the habitable zone of Proxima Centauri, has further amplified the excitement surrounding this star system. While Proxima Centauri b is tidally locked, meaning one side perpetually faces its star, the possibility of liquid water existing on its surface cannot be ruled out, making it a tantalizing target in the search for habitable worlds. One of the biggest challenges in studying Alpha Centauri is its distance. While 4.37 light-years might seem insignificant on a cosmic scale, it still translates to an enormous distance in human terms. Even traveling at the speed of light, it would take over 4 years to reach the system. This immense distance presents significant hurdles for direct observation and exploration. Despite these challenges, scientists are employing cutting-edge technologies and innovative strategies to learn more about Alpha Centauri. Powerful telescopes, both ground-based and space-based, are being used to search for additional exoplanets within the system and to analyze the atmospheres of known planets. Ambitious projects like Breakthrough Starshot are even exploring the possibility of sending tiny, laser-propelled spacecraft to Alpha Centauri, potentially allowing us to obtain close-up images and data within our lifetimes. The allure of Alpha Centauri extends beyond the realm of scientific exploration. It fuels the imagination and inspires dreams of interstellar travel, colonization, and encountering other civilizations. The very idea that a potentially habitable planet orbits the closest star to our own raises profound questions about our place in the universe and the possibility of life beyond Earth. As technology continues to advance and our understanding of the cosmos deepens, Alpha Centauri will undoubtedly remain a focal point of scientific research and a source of inspiration for generations to come. The secrets held within this triple star system may one day unlock some of the universe's greatest mysteries, solidifying its place as a cornerstone in our quest to understand our cosmic neighborhood and our place within it. Andromeda is the closest spiral galaxy to the Milky Way. Andromeda, our cosmic neighbor, holds the title of being the closest large spiral galaxy to our own Milky Way. This means that, of all the grand pinwheel-shaped galaxies scattered across the observable universe, Andromeda is the one situated nearest to us. While there are smaller, irregular galaxies closer to the Milky Way, like the Magellanic Clouds, Andromeda is the closest spiral, a classification that denotes its impressive size and well-defined structure. The sheer proximity of Andromeda makes it a subject of intense study and fascination for astronomers, offering invaluable insights into galaxy formation, evolution, and interactions. Located approximately 2.5 million light-years away, Andromeda is close in cosmic terms. To put this into perspective, a light-year is the distance light travels in 1 year, which is roughly 5.88 trillion miles. Even with such a vast distance, the light from Andromeda is visible to the naked eye under extremely dark skies, appearing as a faint, fuzzy patch. This faint glow represents the combined light of hundreds of billions of stars within Andromeda. Think about that. The light you see has been traveling for 2.5 million years, starting its journey long before humans walked the Earth. Andromeda is a behemoth, even larger than our own Milky Way. It is estimated to contain 1 trillion stars, more than double the number in our galaxy. Its immense size contributes to its brightness and visibility from Earth. The galaxy's spiral arms are tightly wound and filled with dust, gas, and active star-forming regions, giving it a majestic, swirling appearance in astronomical images. Studying these star-forming regions helps scientists understand the processes by which stars are born and evolve. One of the most captivating aspects of Andromeda is its inevitable collision with the Milky Way. Astronomers predict that in about 4.5 billion years, the gravitational pull between the two galaxies will bring them crashing together. This collision is not something to fear, however. Space is vast, and the stars within the galaxies are so far apart that they are unlikely to collide directly. Instead, the galaxies will merge, undergoing a dramatic transformation that will reshape the night sky. The collision will likely result in the formation of a new, giant elliptical galaxy, which some have nicknamed Milkomeda. Scientists have gathered substantial evidence supporting the impending collision by observing the movement of Andromeda. Using advanced techniques, they've measured its velocity and trajectory, confirming that it is indeed heading straight towards us. While 4.5 billion years is a timescale that far exceeds human comprehension, the certainty of this cosmic event allows scientists to study and model the potential outcomes. Furthermore, Andromeda hosts a supermassive black hole at its center, much like the Milky Way. This black hole is millions of times more massive than our Sun and plays a significant role in the galaxy's dynamics. By studying the behavior of stars and gas near Andromeda's central black hole, astronomers can gain a better understanding of the powerful forces that shape galaxies. Observing the interaction between the black hole and its surroundings provides clues about the black hole's properties and its influence on the galaxy's evolution. Andromeda's status as our nearest spiral neighbor makes it an invaluable resource for astronomical research. It provides a close-up view of a galaxy similar to our own, allowing us to study galactic structures, star formation, and the behavior of supermassive black holes in detail. As technology advances, future observations of Andromeda will undoubtedly unveil even more secrets about the universe and our place within it. Astronauts' bones weaken in space. Astronauts venturing into the vast expanse of space face numerous challenges, and among the less apparent yet significant ones is the weakening of their bones. This phenomenon, known as spaceflight-induced bone loss, is a fascinating consequence of the unique environment astronauts inhabit. On Earth, gravity constantly exerts a force on our bodies, compelling us to bear weight and stimulating bone formation. Bones are dynamic tissues, continuously breaking down and rebuilding themselves in a process called bone remodeling. This remodeling is influenced by various factors, including mechanical stress, hormonal balance, and nutrient intake. When we walk, run, or even stand, our bones experience mechanical loading, which signals them to strengthen and increase their density. In the microgravity environment of space, however, the mechanical loading on bones is drastically reduced. Astronauts float effortlessly, no longer needing to support their body weight against gravity. This lack of weight-bearing stimulus disrupts the normal bone remodeling process. The rate of bone breakdown, or resorption, exceeds the rate of bone formation, leading to a net loss of bone mass and density. The weight-bearing bones of the lower body, such as the hips and legs, are particularly affected. Studies have shown that astronauts can lose bone mass at a rate of 1 to 2% per month during long-duration space flights. This rate of bone loss is comparable to that experienced by individuals with osteoporosis on Earth, a condition characterized by weakened bones and increased risk of fractures. The consequences of spaceflight-induced bone loss can be significant. Astronauts returning from extended missions may be at higher risk of fractures, especially in the spine and hips. Moreover, the lost bone may not be fully recovered even after returning to Earth's gravity. The long-term effects of repeated spaceflights on bone health are still being investigated, but concerns exist about the potential for cumulative bone loss and increased fracture risk later in life. To mitigate the effects of bone loss in space, astronauts engage in a variety of countermeasures. Exercise is crucial, and astronauts spend several hours each day performing resistance exercises on specialized equipment designed to simulate weight-bearing activities. These exercises help to stimulate bone formation and reduce bone resorption. Nutritional interventions also play a role. Astronauts consume diets rich in calcium and vitamin D, essential nutrients for bone health. Scientists are also exploring the potential of pharmaceutical interventions to prevent or reverse bone loss in space. Bisphosphonates, drugs commonly used to treat osteoporosis, have shown promise in reducing bone resorption in astronauts. Further research is ongoing to develop more effective countermeasures and better understand the mechanisms underlying spaceflight-induced bone loss. By addressing this challenge, we can ensure the long-term health and well-being of astronauts as they explore the cosmos and push the boundaries of human space exploration. Black holes distort time and space. Black holes, those enigmatic cosmic entities, wield a power so profound that they warp the very fabric of spacetime. Imagine space and time as a smooth, continuous sheet, like a vast trampoline. When a massive object, such as a star, is placed on this sheet, it creates a dip, causing nearby objects to roll towards it. A black hole, however, is like an infinitely deep pit, an abyss that distorts the sheet beyond comprehension. Its gravitational pull is so intense that nothing, not even light, can escape its clutches once it crosses a certain boundary known as the event horizon. The distortion of space around a black hole is relatively straightforward to visualize. Objects approaching a black hole are stretched and squeezed, a process often referred to as spaghettification. This occurs because the gravitational force is significantly stronger on the side of the object closest to the black hole than on the side farther away. Imagine a spacecraft falling towards a black hole feet first. The gravitational force on its feet would be so much stronger than on its head that the spacecraft would be elongated into a long, thin strand. The distortion of time, however, is a more mind-bending concept. Time itself is not absolute, but is relative to the observer's frame of reference and the gravitational field they are experiencing. Near a black hole, gravity is incredibly strong, and this intense gravity causes time to slow down relative to an observer far away from the black hole. To an observer watching someone fall into a black hole, the person would appear to move slower and slower as they approach the event horizon. Their movements would seem to stretch out, their light would become redder, and eventually they would appear to freeze completely at the event horizon, fading from view. From the perspective of the person falling into the black hole, their experience of time would be quite different. They would not necessarily perceive time slowing down for themselves. Instead, they would continue to experience time passing normally, even as they crossed the event horizon. However, their fate would be sealed. Once inside, they would be inevitably drawn towards the singularity, the point of infinite density at the black hole's center, where the laws of physics as we know them break down. The time distortion near black holes has been experimentally verified, albeit on a much smaller scale, using incredibly precise atomic clocks. These experiments demonstrate that clocks at higher altitudes, where gravity is slightly weaker, tick faster than clocks at lower altitudes. While the differences are minuscule, they confirm Einstein's theory of general relativity, which predicts the warping of spacetime by massive objects. Black holes are the ultimate manifestation of this phenomenon, creating regions where time and space are distorted beyond our everyday experience. Studying these celestial giants provides invaluable insights into the fundamental nature of gravity and the intricate workings of the universe. Black holes have gravity so strong even light can't escape. Black holes, cosmic entities of unparalleled intrigue, stand as a testament to the universe's capacity for the extreme. Imagine a region in space where gravity reigns supreme, a force so intense that nothing, not even light, can break free from its relentless grasp. This, in essence, is a black hole. The very name evokes a sense of mystery, a void in the fabric of space-time where our understanding of physics teeters on the brink. The formation of a black hole is a dramatic affair, often signaled by the death throes of a massive star. When a star significantly larger than our sun exhausts its nuclear fuel, the outward pressure that once sustained it against gravity's inward pull collapses. The star's core implodes violently, crushing itself into an infinitesimally small point known as a singularity. This singularity is the heart of the black hole, possessing virtually all of the original star's mass concentrated into a volume of zero size. Surrounding the singularity is the event horizon, the black hole's point of no return. It is not a physical surface, but rather a boundary defined by the strength of the black hole's gravity. Anything that crosses the event horizon, be it matter, light, or even information, is forever trapped within the black hole's clutches. The event horizon's size depends directly on the black hole's mass. The more massive the black hole, the larger its event horizon. One of the most fascinating aspects of black holes is their impact on spacetime. According to Einstein's theory of general relativity, massive objects warp the fabric of spacetime around them. Black holes, being incredibly dense, create extreme distortions, bending light rays and altering the flow of time. Imagine spacetime as a vast sheet, and a black hole as a bowling ball placed upon it. The bowling ball creates a deep indentation, drawing nearby objects towards it. Light, following the curves of spacetime, is also pulled towards the black hole, eventually reaching the event horizon and disappearing forever. Despite their reputation as cosmic vacuum cleaners, black holes are not simply destroyers. They play a significant role in the evolution of galaxies. Supermassive black holes, millions or even billions of times the mass of our sun, reside at the centers of most galaxies. These behemoths exert a powerful influence on their surroundings, shaping the distribution of stars and gas within the galaxy. They can also trigger bursts of intense energy when matter falls into them, creating quasars, the most luminous objects in the universe. Scientists continue to study black holes to unravel the mysteries of gravity and the nature of spacetime. They utilize telescopes that can detect the radiation emitted by matter swirling around black holes, as well as gravitational wave detectors that can sense the ripples in spacetime caused by the mergers of black holes. These observations provide invaluable insights into the behavior of matter under extreme conditions, pushing the boundaries of our knowledge of the universe. Black holes remain one of the most enigmatic and captivating phenomena in the cosmos, serving as a constant reminder of the universe's boundless capacity to surprise and inspire awe. Earth's atmosphere extends 6,200 miles above the surface. The Earth's atmosphere, the gaseous envelope surrounding our planet, is far more expansive than most people realize. We often think of the atmosphere as the air we breathe near the surface, but it actually extends a staggering 6,200 miles above the Earth's surface. This vast expanse is not a uniform blanket, but rather a series of layers, each with distinct characteristics and playing crucial roles in protecting life and regulating our planet's climate. Imagine traveling upwards from the ground. The first layer, the troposphere, is where we live and where most weather phenomena occur. This layer extends only about 7 to 12 miles above the surface, a relatively thin skin compared to the atmosphere's total reach. Above the troposphere lies the stratosphere, home to the ozone layer. This critical layer absorbs the majority of the sun's harmful ultraviolet radiation, shielding life on Earth from its damaging effects. The stratosphere is also where jet aircraft often fly, taking advantage of the stable air conditions. As we ascend further, we enter the mesosphere, a layer characterized by extremely cold temperatures. This layer burns up most meteors entering the Earth's atmosphere, creating the spectacular streaks of light we know as shooting stars. Above the mesosphere is the thermosphere, where temperatures begin to rise again, reaching incredibly high levels. The thermosphere is home to the International Space Station and many satellites orbiting the Earth. Auroras, the mesmerizing displays of light seen near the Earth's poles, also occur in the thermosphere, caused by charged particles from the Sun interacting with the Earth's magnetic field. Finally, we reach the exosphere, the outermost layer of the atmosphere. This layer gradually fades into the vacuum of space, with no clear boundary defining where the atmosphere ends and outer space begins. In the exosphere, gas molecules are very sparse and can travel hundreds or even thousands of miles before colliding with another molecule. Some of these molecules gain enough energy to escape the Earth's gravity altogether and drift off into space. The Earth's atmosphere is not just a static entity. It is constantly interacting with the Sun, the Earth's surface, and even life itself. The Sun's energy drives atmospheric circulation, creating winds and weather patterns that distribute heat around the globe. The atmosphere also plays a critical role in the water cycle, transporting water vapor from the oceans to the land, where it falls as rain and snow. Furthermore, the atmosphere contains greenhouse gases, such as carbon dioxide and methane, which trap heat and keep the Earth warm enough to support life. However, human activities are increasing the concentration of these gases, leading to climate change and its associated challenges. Understanding the full extent and complexity of the Earth's atmosphere is essential for addressing environmental issues and ensuring the long-term sustainability of our planet. From protecting us from harmful radiation to regulating our climate, the atmosphere is a vital resource that we must strive to protect and preserve. While we may only directly experience the air near the surface, the atmosphere's influence extends far beyond, reaching thousands of miles into space and shaping the conditions that make life on Earth possible. Earth rotates at 1,000 miles per hour. Earth's spin, often overlooked in our daily lives, is a remarkable cosmic ballet that dictates our days and nights. Our planet gracefully pirouettes on its axis at an astonishing speed of approximately 1,000 miles per hour at the equator. This mind-boggling velocity means that if you were standing on the equator, you would be hurtling through space at the speed of a commercial jet airplane. Now, imagine this immense scale. The Earth, a sphere with a circumference of about 24,901 miles at the equator, completes one full rotation in roughly 24 hours. Dividing the circumference by the time it takes for one rotation reveals the speed at which locations on the equator are moving. This speed decreases as you move towards the poles because the circumference around the Earth gets smaller. So, while someone standing at the equator is whisked through space at 1,000 miles per hour, someone closer to the North or South Pole is moving much slower. But if we are spinning so fast, why don't we feel it? The answer lies in inertia and gravity. Inertia is the tendency of an object to resist changes in its state of motion. Because we are moving along with the Earth, at the same speed, inertia keeps us from feeling the rapid rotation. We are also held firmly to the ground by Earth's gravity. This prevents us from being flung off into space, despite the considerable speed. It is also interesting to note that the rotation of the Earth isn't perfectly constant. The Earth's rotation experiences slight variations due to factors like the movement of molten iron within the planet's core, the gravitational pull of the Moon and Sun, and even events on the Earth's surface, such as earthquakes and large-scale weather systems. These changes are tiny, only affecting the length of the day by milliseconds, but they are measurable and studied by scientists. The speed of Earth's rotation has not always been the same. Billions of years ago, when Earth was young, it spun much faster, resulting in days that were only a few hours long. Over eons, the Moon's gravitational interaction with Earth has gradually slowed the planet's rotation, a process known as tidal braking. The Earth's rotation is intimately linked to our perception of time. Without this constant spin, we would not have the predictable cycle of day and night that governs our lives. It also influences global weather patterns, ocean currents, and the Earth's magnetic field, which protects us from harmful solar radiation. The fact that we are all passengers on this giant spinning ball, hurtling through space at 1,000 miles per hour, is a testament to the incredible forces at play in our universe. It is a reminder that, even in our seemingly stable world, there is constant motion and change occurring on a cosmic scale. Fruit flies were the first living beings in space. Fruit flies, those tiny ubiquitous insects often found buzzing around overripe fruit, hold a remarkable place in the history of space exploration. They weren't astronauts, nor were they glamorous test subjects, but these minuscule creatures were, in fact, the first living beings sent into space by humans. This pivotal event occurred in 1947, a time when the dream of space travel was still largely confined to the realm of science fiction. The United States, eager to explore the possibilities and perils of venturing beyond Earth's atmosphere, chose fruit flies for a very specific set of reasons. Scientists at the time were deeply interested in understanding the effects of radiation exposure on living organisms. Outer space is permeated with cosmic radiation, a constant bombardment of high-energy particles that can damage DNA and potentially cause mutations. Fruit flies, scientifically known as Drosophila melanogaster, proved to be an ideal subject for this investigation. Their short lifespan, rapid reproduction rate, and relatively simple genetic makeup made them perfect for observing the immediate and long-term consequences of radiation. Any mutations or genetic changes caused by the cosmic rays would become apparent much faster in fruit flies than in larger, more complex animals. The experiment itself was rather rudimentary by today's standards. The fruit flies were contained within a V-2 rocket, a type of missile originally developed by Germany during World War II. These rockets, repurposed for scientific research, were capable of reaching altitudes high enough to enter the edge of space. The rocket carrying the fruit flies ascended to an altitude of approximately 68 miles, or 109 kilometers. While this height isn't considered to be in outer space by all definitions, it was high enough to expose the flies to significant levels of cosmic radiation and explore the effects of near-space conditions. The V-2 rocket flight lasted only a few minutes. After reaching its peak altitude, the rocket descended back to Earth. The fruit flies were recovered unharmed, though undoubtedly a bit disoriented from their brief but historic journey. Scientists then carefully examined the flies to assess the impact of the radiation exposure. The data collected from this experiment, while limited, provided invaluable early insights into the potential dangers of space travel and the effects of radiation on living organisms. This information helped to inform future space missions and contributed to the development of safety protocols for human astronauts. Beyond the scientific benefits, the flight of the fruit flies also marked a significant milestone in humanity's quest to reach for the stars. It demonstrated the feasibility of sending living organisms into space and returning them safely. This success paved the way for further experiments with other animals, eventually leading to the first human spaceflight of Yuri Gagarin in 1961. The humble fruit fly, often overlooked and unappreciated, played a crucial role in laying the groundwork for these extraordinary achievements. Their contribution to the early days of space exploration is a testament to the power of scientific curiosity and the importance of even the smallest creatures in unraveling the mysteries of the universe. They are a reminder that groundbreaking discoveries can sometimes come in the most unexpected packages, or in this case, within a repurposed rocket carrying a tiny contingent of fruit flies. Ganymede is bigger than Mercury. Ganymede, a moon orbiting the gas giant Jupiter, holds a fascinating distinction in our solar system. It is larger than the planet Mercury. This comparison often surprises people, as planets generally dwarf their moons. While Mercury is a fully fledged planet with its own orbit around the Sun, Ganymede is a satellite, gravitationally bound to Jupiter. To fully grasp the significance of this size disparity, Let's explore the dimensions and characteristics of both celestial bodies. Ganymede boasts a diameter of approximately 5,268 kilometers, while Mercury measures roughly 4,880 kilometers across. This makes Ganymede about 8% larger in diameter than Mercury. Imagine holding two balls side by side. Ganymede would be noticeably bigger. However, size isn't everything. While Ganymede wins in terms of diameter, Mercury is significantly more massive. Mercury is composed primarily of dense iron, giving it a much higher density than Ganymede. Ganymede is composed of roughly equal parts silicate rock and water ice. This difference in composition explains why Mercury is much heavier, despite being smaller. The internal structures of these two bodies also contribute to their distinct characteristics. Mercury possesses a large iron core that makes up a significant portion of its volume, surrounded by a silicate mantle and crust. Ganymede, on the other hand, is believed to have a differentiated interior consisting of an iron core, a rocky mantle, and a thick layer of water ice. Interestingly, scientists have found evidence suggesting that Ganymede may even have a subsurface ocean of liquid water sandwiched between layers of ice. This makes Ganymede a particularly intriguing target for future exploration in the search for extraterrestrial life. Another fascinating aspect of Ganymede is its magnetic field. It is the only moon in our solar system known to possess its own magnetosphere, a region of space around the moon dominated by its magnetic field. This magnetic field is likely generated by the movement of molten iron within its core, similar to how Earth's magnetic field is produced. Mercury also has a magnetic field, although it is much weaker than Earth's. The surfaces of Ganymede and Mercury also tell different stories. Mercury's surface is heavily cratered, a testament to the countless impacts it has endured over billions of years. It also has vast smooth plains, likely formed by ancient volcanic activity. Ganymede's surface is a mixture of heavily cratered dark regions and lighter, grooved terrain. The grooved terrain is thought to have formed due to tectonic activity, driven by the moon's icy composition. This makes Ganymede a geologically active moon, unlike Mercury, which is largely considered to be geologically dead. Furthermore, their environments are vastly different. Mercury is a scorching hot planet during the day and bitterly cold at night due to its proximity to the sun and lack of atmosphere. Ganymede, being much farther from the sun and orbiting within Jupiter's magnetosphere, experiences a different kind of environment. It is constantly bombarded by charged particles from Jupiter, which interact with its magnetic field and surface. In conclusion, while Ganymede's size surpasses that of Mercury, these two celestial bodies are fundamentally different in their composition, internal structure, surface features, and environments. Comparing them highlights the diversity and complexity of our solar system and underscores the fact that size is just one of many factors that define a celestial object. Hubble Space Telescope orbits at 350 miles altitude. The Hubble Space Telescope, a marvel of engineering and a window to the cosmos, resides in an orbit approximately 350 miles above the Earth's surface. To truly appreciate this altitude, consider this. Commercial airplanes typically cruise at around 6 miles. That means Hubble is orbiting over 50 times higher than your average jetliner. This lofty perch grants Hubble a significantly clearer view of the universe, unburdened by the majority of Earth's atmospheric distortions that plague ground-based telescopes. Imagine trying to spot a distant ship through a heat haze. That's what astronomers on the ground contend with, and what Hubble cleverly avoids. Orbiting at this altitude means Hubble is not geostationary. Geostationary satellites, like those used for television broadcasting, maintain a fixed position relative to Earth by orbiting at a much higher altitude, approximately 22,000 miles. Hubble, on the other hand, whips around the Earth at a brisk pace, completing one orbit in about 95 minutes. This translates to approximately 15 orbits per day, allowing it to capture a variety of astronomical targets in a relatively short time frame. It's like having a celestial hummingbird flitting around our planet, constantly observing different parts of the universe. The selection of 350 miles was not arbitrary. It represents a sweet spot where the atmosphere is thin enough to minimize drag on the telescope, while still being within a range that allowed for servicing missions by the space shuttle. The atmosphere, even at that altitude, isn't completely absent. Minute amounts of air molecules still exist, and these constantly bombard Hubble, gradually slowing it down over time. This is why the telescope required periodic boosts to maintain its desired orbit. These servicing missions, conducted by astronauts, were not only crucial for maintaining Hubble's altitude, but also for upgrading its instruments and repairing any malfunctions. Think about the sheer audacity of those missions. Astronauts, encased in specialized suits, venturing out of the space shuttle to perform delicate repairs on a multi-billion-dollar instrument hurtling through space at thousands of miles per hour. They were essentially mechanics working on a race car while it was still on the track. The success of these missions is a testament to human ingenuity and our unwavering desire to unravel the mysteries of the universe. Hubble's orbit also plays a critical role in its power generation. The telescope relies on solar panels to convert sunlight into electricity, which powers its instruments, computers, and communication systems. Orbiting the Earth allows Hubble to regularly pass into and out of Earth's shadow. When in sunlight, the solar panels are fully operational, charging the batteries that power the telescope during periods of darkness. This cycle of light and darkness is essential for maintaining a stable power supply and ensuring the continuous operation of the telescope. Furthermore, this specific altitude mitigates certain risks associated with space debris. While space is vast, it's also becoming increasingly cluttered with discarded satellites, rocket parts, and other man-made objects. These objects, traveling at tremendous speeds, pose a significant threat to operational spacecraft. Hubble's altitude is monitored closely to avoid potential collisions with debris. While the risk cannot be entirely eliminated, the chosen orbit provides a reasonable balance between maximizing observational capabilities and minimizing the risk of damage from space debris. So, the next time you see a breathtaking image captured by the Hubble Space Telescope, remember that it all began with a carefully chosen altitude, 350 miles above our home planet, a testament to human innovation and a commitment to exploring the cosmos. IC 1101 has the largest known black hole. IC 1101 is an extraordinary supergiant elliptical galaxy, a cosmic behemoth residing approximately 1.045 billion light-years away in the Abell 2029 galaxy cluster. What truly sets IC 1101 apart is not just its immense size, estimated to be around 6 million light-years across, making it the largest known galaxy in the observable universe, but also the colossal supermassive black hole lurking at its core. This black hole isn't just big, it's the most massive black hole ever discovered, a true heavyweight champion of the cosmos. Scientists estimate this central black hole's mass to be staggering, somewhere in the range of 40 to 100 billion times the mass of our Sun. To put that into perspective, the supermassive black hole at the center of our own Milky Way galaxy, Sagittarius A dot, is a comparatively lightweight 4 million solar masses. Imagine the gravitational influence of an object tens of billions of times more massive than our Sun. It's a truly mind-boggling concept. The sheer size of IC 1101 and its central black hole begs the question, how did such a colossal structure come to be? The prevailing theory suggests that IC 1101 isn't a single, pristine galaxy formed in isolation. Instead, it's believed to be the result of numerous galactic mergers over billions of years. Think of it as a cosmic cannibal, gradually consuming smaller galaxies and incorporating them into its own structure. Each merger would have contributed to the galaxy's overall mass, and importantly, to the growth of its central black hole. As galaxies merge, their central black holes can also merge, creating even larger black holes. This process, repeated over countless epochs, could explain the extraordinary size of the black hole at the heart of IC 1101. The galactic mergers would have provided a continuous supply of gas and dust, fueling the black hole's growth and allowing it to reach its record-breaking mass. The environment surrounding IC 1101 is also crucial to understanding its evolution. Located within the Abell 2029 cluster, IC 1101 is surrounded by a dense, hot intergalactic medium. This hot gas, heated to millions of degrees Celsius, exerts pressure on the galaxy, potentially influencing its star formation and overall structure. The interaction between IC 1101 and the intracluster medium might have also played a role in stripping gas from smaller galaxies falling into the cluster, further contributing to the galaxy's growth through cannibalism. While scientists have a good understanding of the processes that likely contributed to the formation of IC 1101 and its supermassive black hole, some mysteries remain. For example, the exact details of the galactic merger history are still under investigation. Astronomers continue to study IC 1101 using powerful telescopes across the electromagnetic spectrum, hoping to uncover more clues about its past and shed light on the processes that govern the formation and evolution of the largest galaxies and black holes in the universe. Understanding IC 1101 provides invaluable insights into the extreme limits of galactic and black hole growth, pushing the boundaries of our knowledge about the cosmos. Jupiter's Great Red Spot has existed for 400 years. Jupiter's Great Red Spot, a colossal storm larger than Earth itself, is a mesmerizing feature of our solar system and a testament to the immense power of nature. This swirling vortex of crimson clouds has raged on Jupiter for at least 400 years, making it one of the longest-lasting known storms in the universe. Imagine a storm system that dwarfs our entire planet, persisting for centuries. That's the sheer scale and longevity we're talking about. The Great Red Spot isn't just some small weather disturbance. It's a persistent anticyclone, a high-pressure system where winds spiral inward and upward. These winds reach incredible speeds, gusting up to 430 kilometers per hour, far exceeding the most powerful hurricanes on Earth. These ferocious winds are responsible for the spot's distinct reddish hue, likely caused by chemical reactions involving ammonia and sulfur compounds in Jupiter's upper atmosphere. The exact chemical composition responsible for the color is still a subject of scientific debate, adding another layer of mystery to this Jovian wonder. While the Great Red Spot has remained a prominent feature of Jupiter for centuries, it's not static. Observations over time reveal that the spot is actually shrinking. In the late 1800s, astronomers estimated its size to be about 3 times the diameter of Earth. Now it's roughly 1.3 times Earth's diameter. Scientists aren't entirely sure why the spot is shrinking, but one theory suggests that it's losing energy due to interactions with other atmospheric features on Jupiter. Despite the shrinking, the Great Red Spot remains a force to be reckoned with, still capable of engulfing our entire planet within its swirling cloud bands. The persistence of the Great Red Spot also raises fascinating questions about Jupiter's atmosphere. Unlike Earth, Jupiter is a gas giant, lacking a solid surface. This means that the storm isn't anchored to any geographical features, allowing it to persist for centuries without dissipating. The energy that fuels the Great Red Spot likely comes from Jupiter's internal heat, combined with the planet's rapid rotation, which generates powerful atmospheric currents. This combination of factors creates a stable environment that allows the storm to thrive. Studying the Great Red Spot provides valuable insights into the dynamics of gas giants and the behavior of planetary atmospheres. By analyzing the storm's size, shape, color, and wind speeds, scientists can learn more about the processes that drive weather patterns on Jupiter and other similar planets. Spacecraft missions like Voyager, Galileo, and Juno have provided close-up images and data that have revolutionized our understanding of the Great Red Spot. Juno, in particular, has allowed scientists to probe the storm's depth and internal structure, revealing that it extends hundreds of kilometers below the cloud tops. The future of the Great Red Spot remains uncertain. While it's been shrinking, it shows no signs of disappearing entirely. It's possible that the spot could eventually dissipate, but it could also stabilize at a smaller size or even grow again in the future. Regardless of its ultimate fate, the Great Red Spot will continue to captivate our imaginations and serve as a reminder of the incredible power and diversity of our solar system. It stands as a visible beacon of the alien and dynamic weather systems that operate on a scale far beyond our everyday experiences on Earth. The fact that we can observe a storm that has persisted for centuries, larger than our own planet, highlights the ongoing discoveries and mysteries that await us as we continue to explore the cosmos. Light travels at 186,282 miles per second. Light, an essential component of our universe, possesses a characteristic that continues to fascinate scientists and the general public alike: its unparalleled speed. Light travels at an astonishing 186,282 miles per second. This seemingly simple statement holds profound implications for our understanding of the cosmos, our perception of time, and the way we interact with the world around us. To truly grasp the immensity of this velocity, consider the following perspective. In just 1 second, a beam of light could circumnavigate the Earth nearly 7.5 times. This incredible feat highlights the sheer distance light can cover in a minuscule fraction of time. But how was this remarkable speed even measured? Historically, determining the speed of light presented a formidable challenge. Early attempts often relied on astronomical observations, such as timing eclipses of Jupiter's moons. However, these methods yielded only approximate values. It wasn't until the 19th century that significant breakthroughs occurred. Physicists like Hippolyte Fizeau and Léon Foucault devised ingenious experiments involving rotating toothed wheels and mirrors, respectively. These experiments allowed for increasingly precise measurements of the time it took for light to travel known distances, ultimately leading to a more accurate determination of its speed. The constant speed of light in a vacuum, often denoted by the letter c, is a cornerstone of modern physics, particularly in Einstein's theory of relativity. According to this theory, the speed of light is not only constant, but also represents the ultimate speed limit in the universe. No object or information can travel faster than light. This fundamental principle has far-reaching consequences, affecting our understanding of space, time, gravity, and the nature of reality itself. Consider the implications for astronomy. When we observe distant galaxies through powerful telescopes, we are essentially looking back in time. The light from these galaxies has traveled for billions of years to reach our eyes, meaning that we are seeing them as they existed in the distant past. The farther away an object is, the older the light we observe from it. This time delay introduces a fascinating aspect to our exploration of the universe, allowing us to study the evolution of cosmic structures over vast stretches of time. Furthermore, the speed of light plays a crucial role in technologies we rely on every day. Global Positioning System satellites use radio signals which travel at the speed of light to determine our location on Earth. Even the Internet relies on fiber optic cables that transmit data as pulses of light. The speed at which these signals travel directly affects the speed at which we can access information and communicate with others around the world. As our understanding of the universe continues to evolve, the speed of light remains a fundamental constant that underpins much of our knowledge. Its implications extend far beyond the realm of physics, influencing our understanding of time, space, and the very nature of reality. The simple fact that light travels at 186,282 miles per second continues to inspire awe and wonder, reminding us of the boundless mysteries that the universe holds. Mars has 2 moons, Phobos and Deimos. Mars, the rusty red planet, boasts 2 unique celestial companions, Phobos and Deimos. Unlike our moon, these Martian moons are not spherical, majestic orbs. Instead, they are small, irregularly shaped rocks, resembling asteroids more than traditional moons. Phobos, the larger of the 2, is only about 22 kilometers in diameter, while Deimos is even smaller, measuring roughly 12 kilometers. Their diminutive size and peculiar shapes immediately set them apart from most of the other moons in our solar system. The surfaces of Phobos and Deimos are heavily cratered, bearing witness to a long history of cosmic impacts. These craters provide valuable clues about the moon's ages and the bombardment they have endured over billions of years. Phobos, in particular, exhibits a prominent feature called Stickney crater, a massive impact crater that stretches almost half the length of the moon. The impact that created Stickney crater must have been incredibly powerful, nearly shattering Phobos completely. Perhaps the most fascinating aspect of these Martian moons is their unusual orbital behavior. Phobos orbits Mars incredibly closely, whizzing around the planet 3 times a day. This proximity comes with a consequence. Phobos is gradually spiraling inward towards Mars. Scientists predict that in a few tens of millions of years, Phobos will either crash into the Martian surface or be torn apart by the planet's gravity, forming a ring around Mars. Deimos, on the other hand, orbits much farther away and is slowly drifting away from Mars. The origin of Phobos and Deimos is still a topic of debate among scientists. One prevailing theory suggests that they are captured asteroids, drawn in by Mars' gravitational pull billions of years ago. This theory is supported by their irregular shapes and composition, which are similar to those of asteroids found in the asteroid belt between Mars and Jupiter. However, another theory proposes that they form from debris ejected into space after a large impact on Mars. This impact theory could explain the moon's composition and their synchronized orbits around Mars' equator. Despite their relatively small size and distance from Earth, Phobos and Deimos have captured the imagination of scientists and space enthusiasts for decades. They represent intriguing targets for future exploration missions, offering the potential to unlock secrets about the early solar system, the history of Mars, and the formation of moons in general. Studying these Martian moons up close could provide valuable insights into the composition of asteroids, the processes of planetary accretion, and the potential for resources that could be utilized by future human explorers on Mars. Furthermore, the unique orbital dynamics of Phobos and its eventual fate offer a rare opportunity to observe the destruction of a moon firsthand, providing valuable data for understanding the forces that shape our solar system. Phobos and Deimos, though small and unassuming, are key pieces in the puzzle of understanding Mars and its place in the cosmos. Mars missions take about 9 months. Traveling to Mars is no quick jaunt. It is a voyage that typically consumes around 9 months. This lengthy duration is not merely an arbitrary figure, but a carefully calculated consequence of the orbital mechanics governing our solar system. The planets, including Earth and Mars, are in constant motion, each tracing its own path around the Sun at varying speeds. Because of this, the distance between Earth and Mars is in a perpetual state of flux, fluctuating from a minimum of about 33.9 million miles to a maximum of roughly 250 million miles. The most efficient time to launch a mission to Mars, in terms of fuel consumption and travel time, is during a period known as an opposition. This is when Earth and Mars are aligned in such a way that they are relatively close to each other. Even during these opportune moments, the distance remains substantial, dictating the lengthy travel time. The 9-month estimate is based on a Hohmann transfer orbit, which is the most fuel-efficient trajectory to reach Mars. This orbit involves a carefully calculated elliptical path that intercepts Mars' orbit at the right point in time. However, the actual travel time can vary depending on several factors, including the specific trajectory chosen, the launch window, and the spacecraft's velocity. Some missions may take slightly longer, perhaps 10 or even 11 months, while others might be completed in a little under 9 months. The duration is a trade-off between speed, fuel efficiency, and the overall mission objectives. Speeding up the journey would necessitate a significant increase in fuel consumption, which would translate to a heavier spacecraft and higher launch costs. The extended duration of a Mars mission presents a unique set of challenges for the crew. Spending 9 months in the confines of a spacecraft, subjected to the harsh environment of space, requires meticulous planning and execution. The crew must be carefully selected and trained to cope with the psychological and physiological effects of prolonged space travel. This includes maintaining physical fitness, managing stress, and maintaining social cohesion within the confined environment. Moreover, the spacecraft must be equipped with life support systems capable of providing the crew with breathable air, potable water, and nutritious food for the entire duration of the journey. Radiation shielding is also critical to protect the crew from the harmful effects of cosmic radiation and solar flares. Redundancy in essential systems is crucial to mitigate the risk of equipment failure during the long journey. The 9-month travel time also has implications for communication between Earth and the spacecraft. Due to the vast distance, there is a significant time delay in transmitting signals, often ranging from a few minutes to more than 20 minutes. This delay necessitates a high degree of autonomy for the spacecraft and its crew, as real-time communication with mission control is not always possible. The crew must be capable of making independent decisions and resolving problems on their own. In essence, the approximately 9-month travel time to Mars is not just a number, it's a defining factor that shapes the entire mission, influencing spacecraft design, crew selection, and operational strategies. It underscores the immense challenges and incredible feats of engineering required to explore our neighboring planet. It represents both a significant obstacle and an exciting opportunity to push the boundaries of human exploration and scientific discovery. Mars' temperature varies from -125°C to 20°C. Mars, the red planet, holds many secrets and fascinating characteristics, and among them is its wildly fluctuating temperature. Imagine a world where, depending on the time of day and the season, you could experience temperatures ranging from a frigid -125°C to a relatively balmy 20°C. This extreme variation is one of the most intriguing aspects of the Martian climate, setting it apart from our more stable terrestrial environment. Several factors contribute to this dramatic temperature swing. Firstly, Mars has a very thin atmosphere, only about 1% as dense as Earth's. This thin atmosphere provides very little insulation, meaning the planet is unable to retain heat effectively. During the day, the sun's rays warm the surface, but as soon as the sun begins to set, that heat quickly radiates away into space. Unlike Earth, where a thicker atmosphere traps heat, creating a more gradual temperature change, Mars loses its warmth almost immediately. The thin atmosphere also means there are fewer molecules to absorb and distribute heat evenly across the planet. Secondly, the Martian soil has low thermal inertia. Thermal inertia is a measure of how quickly a material heats up or cools down in response to changes in temperature. Materials with high thermal inertia, like water, heat up and cool down slowly, while materials with low thermal inertia, like sand, heat up and cool down rapidly. The Martian surface, composed largely of dust and rock, heats up quickly during the day, but loses that heat just as quickly at night. This contributes to the large temperature difference between day and night. Thirdly, Mars has a significant axial tilt, similar to Earth's. This tilt causes seasons on Mars, just as it does on Earth. During the Martian summer, the hemisphere tilted towards the sun experiences longer days and more intense sunlight, leading to warmer temperatures. Conversely, the hemisphere tilted away from the sun experiences winter, with shorter days and much colder temperatures. The difference in temperature between summer and winter is also amplified by the thin atmosphere and the soil's low thermal inertia. The highest temperature of 20°C can typically be reached near the equator during the Martian summer. This temperature might seem pleasant, but it is important to remember that this is only a surface temperature. The air temperature at even a short distance above the ground would be considerably colder. The lowest temperature of -125°C is generally recorded near the poles during the Martian winter. These extreme cold temperatures are cold enough to freeze carbon dioxide, forming dry ice at the poles. These temperature variations pose significant challenges for future human missions to Mars. Astronauts would need specialized suits and habitats designed to withstand extreme temperature changes. Equipment and machinery would also need to be built to operate reliably in these harsh conditions. Furthermore, the daily temperature swings could have implications for water availability. While water ice has been discovered on Mars, the fluctuating temperatures could affect its stability and accessibility. Despite the challenges, understanding Mars's temperature variations is crucial for planning future exploration and potentially even colonization of the red planet. It's a key piece of the puzzle as we continue to unravel the mysteries of our intriguing neighbor in the solar system. Mercury is the smallest planet with no atmosphere. Mercury, the solar system's innermost planet, claims the title of the smallest, a stark contrast to its once perceived larger size before Pluto's reclassification. This diminutive world, significantly smaller than Earth, also stands out due to its virtually non-existent atmosphere. The absence of a substantial atmosphere is a defining characteristic that profoundly shapes Mercury's environment and surface conditions. The lack of atmosphere means Mercury experiences extreme temperature variations, the most dramatic in the solar system. During the day, when exposed to the full force of the sun's radiation, the surface temperature can soar to a scorching 430 degrees Celsius. Conversely, during the night, without an atmospheric blanket to trap heat, the temperature plummets to a frigid minus 180 degrees Celsius. This colossal temperature swing presents a formidable challenge for any potential life form, and highlights the importance of an atmosphere in regulating planetary temperatures. The reason behind Mercury's atmospheric deficiency is multifaceted. Its small size translates to weak gravity, making it difficult to retain gas molecules. Over billions of years, most of the original atmosphere has likely escaped into space. Solar wind, a constant stream of charged particles from the sun, further strips away any remaining atmospheric gases. The proximity to the sun exacerbates this process as the intense solar radiation energizes gas molecules, giving them enough velocity to overcome Mercury's weak gravitational pull. While Mercury lacks a dense atmosphere in the traditional sense, it does possess an extremely thin exosphere, composed of atoms blasted off the surface by solar wind and micrometeoroid impacts. This tenuous exosphere contains elements like oxygen, sodium, hydrogen, helium, and potassium. Scientists study this exosphere to gain insights into Mercury's surface composition and the processes that shape its environment. The faint glow of sodium, in particular, can be observed from Earth-based telescopes. The absence of a significant atmosphere also impacts Mercury's surface. Unlike Earth, which has an atmosphere that burns up most incoming meteors, Mercury's surface is heavily cratered. The constant bombardment of space rocks, unimpeded by atmospheric friction, has left a lasting mark on the planet's face. These craters provide a window into the solar system's history, revealing the frequency of impacts over billions of years. Despite the seemingly desolate environment, Mercury continues to fascinate scientists. Space missions like Mariner 10 and Messenger, and currently Bepi-Colombo, have provided valuable data about its geology, magnetic field, and tenuous exosphere. Surprisingly, radar observations have revealed evidence of water ice in permanently shadowed craters near the poles, where sunlight never reaches. This discovery suggests that even on a planet with extreme temperature variations, ice can persist in sheltered locations. In essence, Mercury, the smallest planet with no atmosphere, is a world of extremes. Its lack of atmospheric protection exposes it to intense solar radiation and drastic temperature fluctuations, shaping its heavily cratered surface. Yet beneath this harsh exterior lie intriguing mysteries that continue to captivate researchers and challenge our understanding of planetary formation and evolution. Milky Way moves at 1.3 million miles per hour. The Milky Way galaxy, our cosmic home, is not a static entity. It is hurtling through space at an astonishing speed of approximately 1.3 million miles per hour. This mind-boggling velocity equates to roughly 360 miles per second, a speed so immense that it is difficult to grasp in our everyday lives. To put it into perspective, at this speed one could travel from Los Angeles to New York City in a mere 7 seconds. This colossal motion is not random or arbitrary, but rather a consequence of the gravitational forces exerted by the other massive structures in the universe. The primary driver of the Milky Way's movement is the Great Attractor, a region of space teeming with a concentration of galaxies, including the Shapley supercluster, located hundreds of millions of light-years away. The immense gravity of the Great Attractor pulls the Milky Way and other galaxies toward it, influencing their trajectories and contributing significantly to their overall velocities. Interestingly, the seemingly simple statement that the Milky Way is moving at 1.3 million miles per hour is a measurement relative to the cosmic microwave background radiation, often abbreviated as CMB. The cosmic microwave background radiation is the afterglow of the Big Bang, the event that birthed the universe. This radiation permeates all of space and serves as a reference frame against which we can measure the motion of galaxies and other celestial objects. When astronomers speak of the Milky Way's speed, they are essentially referring to its velocity relative to this primordial background radiation. Despite this incredible speed, we, as inhabitants of Earth within the Milky Way galaxy, do not perceive this motion directly. The reason for this lack of perception lies in the fact that we are moving along with the galaxy. Everything within the Milky Way, including our solar system, is subject to the same gravitational forces and is therefore carried along in the same cosmic flow. It is akin to being on a train. While the train may be moving at high speed, the passengers inside do not feel the motion directly unless they look out the window and observe the passing scenery. Furthermore, even though the Milky Way is speeding through space, the distances between galaxies are so vast that the chances of a collision are relatively low. While collisions between galaxies do occur, they are extremely infrequent events, taking place over billions of years. In the distant future, the Milky Way is predicted to collide with the Andromeda galaxy, our nearest large galactic neighbor. This collision, however, is not expected to happen for several billion years, and the effects on our solar system are uncertain. The stars within the galaxies are so far apart that they are unlikely to collide directly. Instead, the galaxies will gradually merge over millions of years, forming a new, larger galaxy. The Milky Way's motion through space is a testament to the dynamic nature of the universe. It is a constant reminder that everything is in motion, from the smallest particles to the largest structures. This understanding of our galaxy's place in the universe and its motion relative to other objects provides valuable insights into the formation and evolution of the cosmos, helping us to unravel the mysteries of our existence. Moon has moonquakes like Earth has earthquakes. The moon, our celestial companion, is not as still and silent as it appears. Just like Earth experiences earthquakes, the moon experiences moonquakes. These lunar tremors, though less frequent and generally weaker than earthquakes, offer valuable insights into the moon's internal structure and geological activity. Moonquakes were first discovered during the Apollo missions when astronauts deployed seismometers on the lunar surface. These instruments detected vibrations and shaking, revealing that the moon is not seismically dead. There are several types of moonquakes, each with a distinct origin and characteristics. Deep moonquakes, occurring about 700 kilometers below the surface, are the most common type. They are believed to be caused by tidal forces exerted by Earth, which subtly deform the moon's interior. These moonquakes are typically weak, but can last for a long time, sometimes up to an hour. Shallow moonquakes, on the other hand, occur much closer to the surface, within 20 to 30 kilometers. These are less frequent, but significantly more powerful than deep moonquakes. Their origin is still debated, but some scientists suspect they are caused by landslides or impacts from meteorites. Interestingly, shallow moonquakes occur in the same locations repeatedly, suggesting that certain regions of the moon are more prone to seismic activity. Another type of moonquake is thermal moonquakes, which are caused by the expansion and contraction of the lunar surface due to the extreme temperature variations between lunar day and night. The moon lacks a substantial atmosphere, resulting in drastic temperature swings, ranging from scorching heat to frigid cold. This temperature difference causes stress on the lunar rocks, leading to small fractures and tremors. Finally, there are impact moonquakes, caused by meteoroid impacts on the moon's surface. The size and intensity of these moonquakes depend on the size and velocity of the impacting object. While moonquakes are generally weaker than earthquakes, they can still be significant. The Apollo seismometers recorded moonquakes with magnitudes ranging from 1 to 5 on the Richter scale. A magnitude 5 moonquake can cause noticeable shaking and potentially trigger landslides. Studying moonquakes provides valuable information about the moon's internal structure, composition, and thermal state. By analyzing the seismic waves generated by moonquakes, scientists can map the boundaries between the moon's crust, mantle, and core. This helps us understand how the moon formed and evolved over billions of years. Moreover, moonquakes are important for future lunar missions. Understanding the frequency, magnitude, and distribution of moonquakes is crucial for designing safe and stable lunar habitats and infrastructure. Engineers need to consider the potential risks posed by moonquakes when constructing buildings, roads, and other structures on the moon. In summary, moonquakes are a fascinating phenomenon that reveals the dynamic nature of our seemingly quiet lunar neighbor. They offer valuable insights into the moon's internal structure and geological processes, and they are essential for planning future lunar exploration and development. More stars exist than grains of sand on Earth. Imagine standing on a beach, the seemingly endless expanse of sand stretching out before you. Each tiny grain, unique in its own way, contributes to the vast landscape under your feet. Now try to fathom counting every single one of those grains across every beach, every desert, and every seabed on Earth. The task appears not only monumental, but practically impossible. Yet, despite the seemingly incomprehensible number of sand grains on our planet, the universe holds an even more staggering secret. There are more stars in the observable universe than all those grains of sand combined. This mind-boggling fact highlights the sheer immensity and wonder of the cosmos. To appreciate this cosmic truth, we must first grapple with the scale of the universe. Our solar system, with its single star, the Sun, and 8 planets, is just a tiny neighborhood within the Milky Way galaxy. This galaxy, a swirling spiral of hundreds of billions of stars, is so vast that light, traveling at approximately 186,000 miles per second, takes over 100,000 years to cross it. Now consider that the Milky Way is not alone. It is just one galaxy among hundreds of billions, possibly trillions of galaxies scattered throughout the observable universe. Each of these galaxies is an island universe, containing countless stars of its own. Astronomers estimate the number of stars in the observable universe based on observations of galaxies and their average star populations. While precise counts are impossible, the estimations are based on solid scientific principles and observations. By studying the light emitted by galaxies, scientists can estimate their mass and, consequently, the number of stars they contain. These estimations are not mere guesses. They are informed calculations based on our current understanding of astrophysics. The comparison to grains of sand helps put this astronomical figure into perspective. Scientists have attempted to estimate the number of sand grains on Earth, arriving at figures that range from several quintillions to over 7.5 quintillion grains. A quintillion is a number with 18 zeros after it. Even at the higher end of these estimates, the number of stars in the observable universe, which is estimated to be in the range of hundreds of sextillions, vastly surpasses the number of sand grains on our planet. A sextillion is a number with 21 zeros after it. This disparity underscores the profound difference between our everyday experience and the cosmic reality that surrounds us. It highlights the limitations of human perception and the challenges we face in comprehending the true scale of the universe. Thinking about the number of stars evokes a sense of awe and wonder, prompting us to contemplate our place in the grand scheme of things. It forces us to confront the possibility of countless other worlds, perhaps teeming with life, orbiting those distant suns. The existence of so many stars also raises profound questions about the potential for life beyond Earth. With each star potentially hosting multiple planets, the probability of other habitable worlds increases dramatically. The search for extraterrestrial life, therefore, becomes not just a scientific endeavor, but a quest to understand our place in a universe teeming with possibilities. The fact that there are more stars than grains of sand on Earth serves as a constant reminder of the vast unknown and the endless potential for discovery that lies beyond our planet. It encourages us to continue exploring, questioning, and pushing the boundaries of human knowledge. Neptune wind speeds reach 1,200 miles per hour. Neptune, the 8th and farthest known planet from the Sun, possesses a captivating atmospheric phenomenon, winds that can reach staggering speeds of 1,200 miles per hour. This makes them the fastest winds recorded in the solar system, even exceeding those found on gas giant Jupiter. Understanding this extreme weather event requires delving into the peculiar dynamics of Neptune's atmosphere. Despite receiving significantly less solar energy than planets closer to the Sun, Neptune's atmosphere is surprisingly dynamic. The exact mechanism driving these intense winds remains a subject of ongoing research, but several factors are believed to contribute. One crucial element is the planet's internal heat. Neptune radiates more than twice the amount of energy it receives from the Sun, suggesting a powerful internal heat source. This internal heat fuels convective processes, creating significant temperature differences within the atmosphere. These temperature gradients, combined with Neptune's rapid rotation, contribute to the formation of strong zonal winds, which flow parallel to the equator. Unlike Earth, which has continents and other geographical features that disrupt wind patterns, Neptune's atmosphere is primarily composed of hydrogen, helium, and trace amounts of methane. This relatively uniform composition allows winds to circulate almost unimpeded across the planet. The lack of a solid surface also means there is no friction to slow the winds down, enabling them to build up to phenomenal speeds. The presence of methane in Neptune's upper atmosphere gives the planet its characteristic blue color. This methane absorbs red light from the sunlight that reaches Neptune, reflecting the blue light back into space. The interaction of sunlight with the upper atmosphere also plays a role in generating energy that drives the planet's weather systems. The Voyager 2 spacecraft, the only spacecraft to have visited Neptune, provided valuable data about its atmosphere and wind speeds. During its flyby in 1989, Voyager 2 captured images of prominent features like the Great Dark Spot, a massive storm system analogous to Jupiter's Great Red Spot. Although the Great Dark Spot has since disappeared, its existence demonstrated the dynamic and turbulent nature of Neptune's atmosphere. Scientists were able to track the movement of clouds and features within the atmosphere, allowing them to measure the wind speeds directly. The findings confirmed that Neptune's winds were indeed the fastest in the solar system. Further observations from Earth-based telescopes and space-based observatories like the Hubble Space Telescope have continued to monitor Neptune's atmosphere. These observations have revealed variations in wind speeds and atmospheric features over time, providing insight into the complex interplay of factors that drive Neptune's weather. Studying Neptune's extreme winds not only helps us understand the dynamics of gas giant atmospheres, but also provides clues about the fundamental processes that govern weather patterns on all planets, including our own. The study of Neptune continues to unveil fascinating details about this distant, icy world and its extraordinary atmospheric phenomena. Neptune year lasts 165 Earth years. Neptune, the mesmerizing blue giant of our solar system, holds many captivating secrets, and among the most striking is the length of its year. A single year on Neptune, the time it takes to complete one orbit around the Sun, stretches out to an astounding 165 Earth years. This staggering duration is a direct consequence of Neptune's immense distance from the Sun. Located approximately 2.8 billion miles away, about 30 times farther than Earth, Neptune journeys along a much larger orbital path. As a result, it takes far longer for Neptune to complete its solar circuit. To truly appreciate the magnitude of Neptune's year, consider this. Someone born on Earth would witness nearly 2 human lifetimes pass before Neptune completes just one revolution around the Sun. Imagine the changes that would occur on Earth during that vast expanse of time. The rise and fall of civilizations, dramatic shifts in technology, and countless generations coming and going, all while Neptune continues its slow, steady trek through space. The sheer length of Neptune's year has profound implications for the planet's seasons. Similar to Earth, Neptune experiences seasons due to the tilt of its rotational axis. However, because a Neptunian year is so long, each season lasts for over 40 Earth years. This means that a single generation of humans might only experience one season on Neptune. These prolonged seasons likely lead to extreme and gradual shifts in the planet's atmospheric conditions, potentially influencing the formation and dissipation of its famous storms. Adding another layer of intrigue, Neptune was only discovered in 1846. Since then, it has not even completed a full orbit around the Sun from the time of its discovery. In 2011, Neptune finally reached the same point in its orbit that it was at when it was first observed by astronomers. This momentous occasion marked the completion of its first full orbit since its discovery, a truly rare and remarkable event. Neptune's extraordinarily long year not only affects the planet itself, but also shapes our understanding of the outer solar system. Its slow orbital speed has implications for the gravitational interactions with other celestial bodies in its vicinity, including its moons and the objects in the Kuiper belt. The gravitational dance between Neptune and these objects plays a role in shaping the structure and dynamics of this distant region of our solar system. Studying Neptune and its lengthy year offers scientists valuable insights into planetary formation, atmospheric dynamics, and the evolution of solar systems. By examining the subtle changes that occur on Neptune over decades, researchers can better understand the complex processes that govern the behavior of gas giants and the intricate workings of our cosmos. Neptune, with its mesmerizing blue hue and incredibly long year, continues to captivate our imaginations and inspire us to explore the vast and mysterious universe. Olympus Mons is the largest volcano in the solar system. Olympus Mons, a colossal shield volcano on Mars, reigns supreme as the largest volcano and highest known mountain in our solar system. Its sheer scale is mind-boggling, dwarfing even the largest volcanoes on Earth. Imagine a mountain nearly 3 times the height of Mount Everest, sprawling across an area comparable to the entire state of Arizona. This is Olympus Mons, a testament to the unique geological forces that have shaped the red planet. The volcano's base extends over 600 kilometers, a distance that would take you days to traverse on foot. Its summit soars to an incredible 25 kilometers above the surrounding Martian plains, piercing the thin Martian atmosphere. One of the most striking features of Olympus Mons is its gently sloping flanks. Unlike the steep conical shape of many Earth volcanoes, Olympus Mons possesses an extremely shallow slope, averaging only about 5%. This is due to the low viscosity of the lava that erupted from the volcano over billions of years. The lava flowed easily across the Martian surface, spreading out over vast distances and creating the volcano's characteristic shield-like shape. Surrounding the base of Olympus Mons is a steep escarpment or cliff that in places reaches heights of up to 8 kilometers. Scientists believe that this escarpment was formed by massive landslides, triggered by the volcano's immense weight pressing down on the Martian crust. The caldera or summit crater of Olympus Mons is another remarkable feature. It is not a single, unified crater, but rather a complex of 6 overlapping calderas, formed by repeated volcanic eruptions and collapses over millions of years. These calderas collectively measure about 85 kilometers wide and 60 kilometers long, offering a glimpse into the volcano's long and dynamic history. The sheer size of Olympus Mons raises intriguing questions about the geological conditions that allowed it to grow to such immense proportions. On Earth, plate tectonics prevent volcanoes from growing too large, as the movement of the Earth's crust constantly shifts the location of volcanic activity. However, Mars lacks plate tectonics, allowing volcanoes to remain stationary over hotspots in the Martian mantle for billions of years. This sustained volcanic activity, combined with the low gravity on Mars and the high eruption rates of low-viscosity lava, enabled Olympus Mons to accumulate vast amounts of material and reach its unprecedented size. Studying Olympus Mons provides valuable insights into the geological processes that have shaped Mars and the differences between the Earth and the red planet. It also fuels our imagination, inspiring us to contemplate the incredible forces that can sculpt planetary landscapes and the potential for volcanic activity in other parts of our solar system. Olympus Mons stands as a silent giant, a testament to the power of volcanic forces, and a reminder of the wonders that await us beyond our own planet. Its existence highlights the fascinating geological diversity found within our solar system. 1 million Earths fit inside the Sun. Imagine our Earth, a vibrant blue marble teeming with life, a place that feels infinitely vast to us. Now, picture 1,000,000 of these Earths. That's the mind-boggling reality of the Sun's size. The fact that 1,000,000 Earths fit inside the Sun is more than just a number. It's a gateway to understanding the sheer scale of our solar system and the dominance of our star. Consider this. The Sun is not just a little bigger. It's a colossal sphere of hot plasma, primarily hydrogen and helium, generating energy through nuclear fusion. Its diameter is roughly 109 times the diameter of Earth. To visualize this, if the Earth were the size of a pea, the Sun would be about the size of a beach ball. Trying to squeeze 1,000,000 peas into a beach ball starts to illustrate the immense volume difference. But why is the Sun so large? The answer lies in its mass. The Sun accounts for approximately 99.86% of the total mass of the entire solar system. This immense mass creates a powerful gravitational pull, compressing the Sun's core to extreme densities and temperatures, conditions necessary for nuclear fusion to occur. This fusion process releases tremendous amounts of energy in the form of light and heat, the very energy that sustains life on Earth. The idea of fitting 1,000,000 Earths inside the Sun also highlights the stark differences in density. The Sun is primarily composed of gas, while Earth is a rocky planet. If we were somehow able to pack 1,000,000 Earths into the Sun, they wouldn't simply float around. They would be subjected to immense gravitational forces and extreme temperatures, ultimately being vaporized and becoming part of the Sun's plasma. Thinking about this space fact allows us to appreciate the Sun's crucial role. Without the Sun's energy, Earth would be a frozen, lifeless world. The Sun's gravity also keeps all the planets in our solar system in orbit, preventing them from drifting off into the vast emptiness of space. Furthermore, this comparison puts our own existence into perspective. We are inhabitants of a relatively small planet, orbiting a star of considerable size, which is just one star among billions in our galaxy, the Milky Way. And the Milky Way is just one galaxy among billions in the observable universe. The sheer scale of the cosmos is humbling and inspiring. So the next time you feel overwhelmed by earthly concerns, remember that 1,000,000 Earths fit inside the Sun. It's a reminder of the vastness of space, the power of our star, and the delicate balance that allows life to thrive on our small, precious planet. It's a thought that shrinks our problems while simultaneously expanding our sense of wonder and possibility. The simple fact is a key to unlocking a deeper understanding of our place in the universe. 1 teaspoon of neutron star weighs 1,000,000,000 tons. Imagine holding a teaspoon in your hand. Now imagine that teaspoon filled not with sugar or salt, but with material from a neutron star. That seemingly small spoonful would weigh approximately 1,000,000,000 tons. To truly grasp the enormity of this weight, consider that a typical car weighs about 1.5 tons. This single teaspoon of neutron star material would weigh as much as about 666 million cars. This astonishing density is a direct result of the incredible forces at play within these cosmic objects. Neutron stars are the collapsed cores of massive stars that have reached the end of their lives. When a star much larger than our Sun runs out of fuel, it can no longer sustain the outward pressure needed to counteract its own gravity. The star then undergoes a catastrophic implosion known as a supernova. During the supernova, the outer layers of the star are violently expelled into space, while the core collapses inward upon itself. The immense gravitational pressure forces protons and electrons to combine, forming neutrons, hence the name neutron star. This process squeezes the entire mass of the star into an incredibly small volume. A typical neutron star has a diameter of only about 20 kilometers, roughly the size of a city, yet it contains more mass than our Sun. To better visualize this, picture our Sun, a colossal ball of gas with a diameter of nearly 1.4 million kilometers. Now imagine squeezing all of that material into a sphere with a diameter of only 20 kilometers. The resulting object would be a neutron star, an object with unfathomable density. The extreme density of a neutron star leads to some fascinating physical properties. The gravitational pull on the surface of a neutron star is so strong that if you were to drop an object from just 1 meter above the surface, it would hit the ground with a speed of about 7.2 million kilometers per hour. The magnetic fields of neutron stars are also incredibly powerful, billions of times stronger than the Earth's magnetic field. Some neutron stars, known as pulsars, emit beams of electromagnetic radiation from their magnetic poles. As the neutron star rotates, these beams sweep across the sky like a lighthouse, creating the pulsating effect that gives pulsars their name. Scientists study neutron stars to learn more about the fundamental laws of physics under extreme conditions. The densities and magnetic fields found in neutron stars are far beyond anything we can create in a laboratory on Earth. By observing and analyzing these objects, astronomers can test our understanding of gravity, nuclear physics, and the behavior of matter at its most extreme. The fact that a teaspoonful of neutron star material weighs 1 billion tons is a testament to the extraordinary forces and densities found in these fascinating celestial objects. They are cosmic laboratories that offer a unique window into the fundamental workings of the universe. Pluto has a heart-shaped glacier. Pluto, once considered the 9th planet in our solar system, holds a captivating secret on its icy surface, a vast, heart-shaped glacier. This remarkable feature, officially named Tombaugh Regio after Clyde Tombaugh, the astronomer who discovered Pluto, dominates the dwarf planet's appearance and presents a fascinating puzzle for scientists to unravel. The left lobe of the heart, a smooth, bright plane called Sputnik Planitia, is the glacier itself. This massive basin spans over 1,000 kilometers and is composed primarily of frozen nitrogen ice mixed with smaller amounts of methane and carbon monoxide ice. These ices are much more volatile than water ice, meaning they can easily turn into gas at Pluto's frigid temperatures, creating a dynamic and constantly evolving landscape. The sheer size and composition of Sputnik Planitia are intriguing. Scientists believe that the basin was likely formed by a massive impact early in Pluto's history. This impact would have excavated a large area, creating a low-lying region where nitrogen ice could accumulate. The nitrogen ice, being denser than the surrounding water ice crust, would have further deepened the basin due to the weight and pressure, creating a positive feedback loop. The smooth, crater-free surface of Sputnik Planitia suggests that it is geologically active. Convection cells within the nitrogen ice drive a constant churning motion, resurfacing the glacier and erasing any impact craters that might have formed. These convection cells are like giant bubbles of ice rising and falling, similar to how heat rises in a pot of boiling water. The process is incredibly slow, but over millions of years, it reshapes the entire surface of the glacier. The heart-shaped glacier also plays a crucial role in Pluto's atmosphere. As the nitrogen ice warms slightly during Pluto's summer, it sublimates, turning directly into gas. This nitrogen gas then contributes to Pluto's thin atmosphere. The atmosphere, in turn, redistributes heat around the dwarf planet, influencing the temperature and stability of the ices on the surface. Furthermore, the presence of methane and carbon monoxide ice mixed with the nitrogen ice adds complexity to the glacier's dynamics. These different ices have varying melting points and sublimation rates, which can create interesting patterns and textures on the surface. The interaction between these different ices is still not fully understood, but scientists are using computer models and data from the New Horizons mission to learn more. The New Horizons spacecraft, which flew past Pluto in 2015, provided invaluable data and images that revolutionized our understanding of this distant world. The high-resolution images revealed the intricate details of Sputnik Planitia, including the convection cells, the varied ice compositions, and the interactions with the surrounding terrain. This mission confirmed that Pluto is not a dead, frozen world, but rather a dynamic and geologically active body with a fascinating and evolving surface. The heart-shaped glacier is not just a visually striking feature. It is a window into the complex processes shaping Pluto's atmosphere, geology, and ultimately its evolution over billions of years. Its study continues to captivate planetary scientists and inspire further exploration of the outer reaches of our solar system. Saturn has over 80 moons. Saturn, the sixth planet from the Sun, is renowned for its breathtaking ring system, but it also possesses another astonishing feature, a vast entourage of moons. The confirmed count of Saturn's moons currently exceeds 80, a number that dwarfs the moon count of other planets in our solar system. This makes Saturn a veritable lunar kingdom, teeming with diverse worlds that hold secrets to the formation and evolution of planetary systems. While our own Earth has only one moon, and Mars has 2 tiny moons, Saturn's collection is a testament to the planet's immense gravitational pull and its history of capturing celestial objects. Many of Saturn's moons are relatively small, irregular in shape, and heavily cratered, suggesting they are captured asteroids or fragments from larger bodies that were shattered by collisions. These smaller moons often orbit far from Saturn, and their orbits can be tilted at odd angles compared to the planet's equator. They act like cosmic crumbs, providing clues to the chaotic events that shaped the outer solar system billions of years ago. However, Saturn also boasts several large, geologically active moons that capture the imagination of scientists and space enthusiasts alike. Titan, Saturn's largest moon, is a world unlike any other in our solar system. It is the only moon with a dense atmosphere, composed primarily of nitrogen, and it has liquid oceans, rivers, and lakes on its surface. However, these are not water bodies, but rather vast expanses of liquid methane and ethane, reflecting the frigid temperatures that prevail on Titan. The Huygens probe, which landed on Titan in 2005, provided invaluable data and images, revealing a landscape shaped by erosion, sedimentation, and possibly even cryovolcanism, where icy materials erupt onto the surface instead of molten rock. Titan's unique environment raises intriguing questions about the potential for life to exist in non-water-based solvents. Enceladus, another fascinating Saturnian moon, is significantly smaller than Titan, but it is no less remarkable. Scientists have discovered that Enceladus possesses a subsurface ocean of liquid water, which is believed to be in contact with a rocky core. This ocean vents into space through geysers located near the moon's south pole, spewing out plumes of water vapor, ice particles, and organic molecules. The Cassini spacecraft flew through these plumes and analyzed their composition, providing strong evidence for hydrothermal activity within Enceladus's ocean, which could potentially provide the energy and chemical ingredients necessary for life. Iapetus, one of Saturn's more distant moons, is characterized by its striking two-toned appearance. One hemisphere is bright and icy, while the other is dark and reddish-brown. This dramatic color contrast is thought to be caused by the accumulation of dark material on the leading hemisphere as it sweeps through space. Iapetus also features a massive equatorial ridge that extends halfway around the moon, giving it an almost walnut-like appearance. The origin of this ridge remains a mystery, but it may be related to the moon's early formation or a past collision. Saturn's moons are not just static, unchanging worlds. They interact with each other and with Saturn's rings in complex ways, shaping their orbits and influencing their geological activity. Some moons act as shepherd moons, gravitationally sculpting the edges of Saturn's rings. Others are locked in orbital resonances, where their orbital periods are related by simple ratios, creating predictable gravitational interactions. The study of Saturn's moons provides valuable insights into the processes that govern the formation and evolution of planetary systems, and it highlights the diversity and dynamism of the celestial bodies that populate our solar system. Saturn rings are made of ice, dust, and rock. Saturn's rings, a celestial spectacle admired by astronomers and stargazers alike, are primarily composed of ice particles, dust, and rocky debris. These rings, far from being solid structures, are more like a cosmic gravel pit, stretching hundreds of thousands of kilometers from the planet. The composition of the rings is overwhelmingly dominated by water ice, estimated to be over 90%. This ice ranges in size from microscopic specks to chunks several meters across, resembling snowballs in space. The remaining material consists of dust, both icy and silicate, and larger rocks, some even comparable in size to small mountains. The presence of silicate dust gives the rings a subtle color variation, with some regions appearing slightly reddish or brownish. One fascinating aspect of Saturn's rings is their immense size relative to their thickness. While the rings span a vast distance around Saturn, they are remarkably thin, typically only a few meters thick in most places. This makes them incredibly fragile and susceptible to disruptions from gravitational forces. Scientists believe that the rings are not ancient relics from the formation of Saturn, but rather relatively young features, perhaps only a few 100 million years old. Their origin remains a topic of ongoing research, with theories suggesting that they may have formed from the breakup of a moon or the remnants of comets and asteroids that ventured too close to Saturn's powerful gravitational field. The rings are not uniformly distributed, but are instead organized into a complex system of thousands of individual ringlets, separated by gaps of varying sizes. The most prominent gaps, such as the Cassini division, are caused by gravitational resonances with Saturn's moons. These moons, acting as shepherds, clear out material from specific regions, maintaining the boundaries of the rings. The interactions between the rings and the moons create intricate patterns and waves within the ring system. The famous F-ring, located on the outer edge of the main ring system, is particularly influenced by the shepherding moons Prometheus and Pandora, which sculpt its shape and prevent it from spreading out. The brightness and visibility of Saturn's rings vary depending on the viewing angle from Earth and the amount of sunlight reflected by the ice particles. When the rings are tilted towards Earth, they appear bright and prominent, but when viewed edge-on, they nearly disappear from sight. This phenomenon occurs roughly every 15 years, as Saturn makes its way around the Sun. The rings are constantly evolving, with collisions between particles, gravitational interactions, and the influx of micrometeoroids shaping their structure and composition. Spacecraft missions, such as Cassini, have provided invaluable data on the rings, revealing their intricate details and dynamic processes. The Cassini spacecraft even plunged through the rings in its final mission, gathering unprecedented information about their composition and structure before ultimately disintegrating in Saturn's atmosphere. The study of Saturn's rings continues to provide insights into the formation and evolution of planetary systems and the complex interactions between gravity, dust, and ice in the vast expanse of space. Space is silent due to lack of air. Space, the vast expanse beyond our planet, is often portrayed in movies and television with dramatic sound effects, but the reality is quite different. Space is a silent realm, a cosmic ocean of tranquility where sound waves cannot travel. This profound silence is due to the almost complete absence of matter, specifically air, in the vacuum of space. Sound, as we understand it, is a vibration that propagates through a medium, whether it be air, water, or a solid material. These vibrations create pressure waves that our ears detect and interpret as sound. In the absence of a medium dense enough to carry these waves, sound simply cannot exist. Think of it like this. Imagine shouting in a crowded room versus shouting in an empty, sealed chamber. In the crowded room, your voice travels through the air, bouncing off people and objects, eventually reaching the ears of those around you. In the empty chamber, your voice will be muffled and quickly fade away, because there is nothing to carry the sound waves. Space is like that empty chamber, only far more vast and devoid of matter. The density of air on Earth at sea level is about 1.2 kilograms per cubic meter. In interstellar space, the density can be as low as a few atoms per cubic meter, an almost perfect vacuum. The implications of this silence are significant. Astronauts working outside their spacecraft cannot hear each other directly. They rely on radio communication, which uses electromagnetic waves that can travel through the vacuum of space. These radio waves are converted into sound inside their helmets, allowing them to communicate effectively. The silence of space also means that explosions, even massive ones like supernovas, are completely silent events. While we can observe the brilliant light and other electromagnetic radiation from these explosions, we would not hear a thing if we were close enough to witness them firsthand. This lack of sound also contributes to the feeling of isolation and otherworldliness that astronauts often experience. The Earth is a noisy place, filled with the sounds of nature, human activity, and technology. In space, all of that disappears, leaving only the hum of the spacecraft and the voices of fellow astronauts inside their helmets. While the silence of space may seem unsettling at first, it can also be a source of profound peace and tranquility. Many astronauts have described the experience of floating in space, surrounded by the silent beauty of the cosmos, as deeply moving and transformative. Interestingly, the silence of space is not absolute. There are regions of space, such as nebulae, where the density of gas and dust is high enough to allow sound waves to propagate, albeit at very low frequencies that are inaudible to the human ear. Scientists can use specialized instruments to detect these sound waves and learn more about the composition and dynamics of these regions. Furthermore, although sound cannot travel through the vacuum of space, vibrations can still be transmitted through solid objects. For example, if an astronaut touches a spacecraft, they may feel vibrations from the engines or other equipment, even though they cannot hear them. While space is predominantly silent, it is not entirely devoid of vibrational energy. Space shuttle launches reach 180 decibels. Space shuttle launches are incredibly powerful events, generating an immense amount of sound. The sound level at launch can reach a staggering 180 decibels. To put that into perspective, prolonged exposure to sounds above 85 decibels can cause hearing damage. At 180 decibels, the sound pressure is so intense that it can cause physical pain and even damage structures. The primary source of this extreme noise is the sheer force of the rocket engines. The space shuttle was powered by 3 space shuttle main engines and 2 solid rocket boosters. These engines combust a tremendous amount of fuel in a very short period, creating a massive expulsion of hot gas. The rapid expansion of these gases generates intense sound waves. The solid rocket boosters were especially loud because they used solid propellant, which burns very quickly and produces a particularly aggressive exhaust. The acoustic environment around a space shuttle launch is further complicated by the reflection of sound waves off the launch pad and surrounding structures. These reflections can amplify the sound levels in certain areas. NASA implemented several noise reduction measures to protect the shuttle and the launch facilities. One crucial measure was a water suppression system. Just before launch, millions of gallons of water were sprayed onto the launch pad. This water instantly vaporized, absorbing a significant amount of the acoustic energy and reducing the overall noise levels. Interestingly, the sound experienced during a space shuttle launch varies depending on your location. Those close to the launch pad experience the full force of the 180 decibel sound. However, the sound levels decreased rapidly with distance. People watching the launch from several miles away heard a much lower, though still impressive, roar. The noise generated by a space shuttle launch was not just a concern for people and structures on the ground. The intense vibrations caused by the sound waves could also damage the shuttle itself. Sensitive electronic components and delicate instruments were particularly vulnerable. To mitigate this risk, the shuttle was designed with special insulation and vibration dampening materials. The crew inside the shuttle also experienced the launch noise, although it was significantly reduced by the shuttle structure and their protective headsets. They primarily felt the intense vibrations. It is important to note that the decibel scale is logarithmic, meaning that an increase of 10 decibels represents a tenfold increase in sound intensity. Therefore, 180 decibels is not just twice as loud as 90 decibels. It is an astronomically greater amount of sound energy. The sound of a space shuttle launch is a testament to the immense power required to overcome Earth's gravity and send a spacecraft into orbit. It is a raw, visceral demonstration of the forces at play in space exploration. The sheer magnitude of the sound serves as a constant reminder of the challenges and triumphs of pushing the boundaries of human achievement. Sputnik 1 was the first artificial satellite. Sputnik 1, launched by the Soviet Union on October 4, 1957, holds the distinguished title of being the first artificial satellite to orbit the Earth. This seemingly simple aluminum sphere, just 58 centimeters in diameter and weighing a mere 83 kilograms, ignited the space age and forever altered the course of history. Its unassuming appearance belied its profound impact. Imagine a beach ball, albeit a highly polished one, silently traversing the heavens, marking humanity's initial foray beyond the confines of our planet. The satellite's primary function was simple: to transmit radio signals back to Earth. It carried 4 whip antennas, each extending outwards, broadcasting a distinctive beep-beep sound at frequencies of 20.005 and 40.002 megahertz. These beeps, detectable by amateur radio operators worldwide, served as undeniable proof of Sputnik's presence and its successful orbit. The simplicity of the technology was deliberate. Soviet scientists aimed for a reliable and straightforward design, prioritizing functionality over complexity, ensuring a higher chance of success in this groundbreaking endeavor. The launch of Sputnik 1 wasn't just a scientific achievement. It was a monumental political and ideological victory for the Soviet Union during the Cold War. The United States, confident in its technological superiority, was caught completely off guard. The beeping signal emanating from Sputnik became a symbol of Soviet prowess, fueling anxieties in the West about a potential technological gap. Schools across America incorporated more science and math into their curriculum, driven by a fear of falling behind. This reaction, dubbed the Sputnik crisis, spurred significant investments in science, technology, engineering, and mathematics, laying the foundation for future American space endeavors. Sputnik 1 completed an orbit around the Earth in approximately 96 minutes, traveling at a speed of about 29,000 kilometers per hour. Its elliptical orbit took it as far as 939 kilometers from Earth and as close as 215 kilometers. The satellite continued transmitting its iconic beeps for 3 weeks, until its batteries died. After 57 days and roughly 1,440 orbits, Sputnik 1 succumbed to atmospheric drag and burned up upon re-entry on January 4, 1958. Despite its short lifespan, Sputnik 1 left an indelible mark on history. It proved that space exploration was not just a dream but a tangible possibility. It paved the way for future satellite missions, including communication satellites, weather satellites, and scientific research platforms. The data collected from Sputnik 1 regarding atmospheric density and radio signal propagation proved invaluable for subsequent spaceflights. The launch of Sputnik 1 also underscored the importance of international cooperation and competition in scientific advancement. While the initial reaction was one of fear and rivalry, it ultimately motivated both the Soviet Union and the United States to push the boundaries of space exploration. The space race, ignited by Sputnik, resulted in remarkable achievements, including the first human in space and the first landing on the Moon. Sputnik 1, the humble beeping sphere, remains a powerful reminder of the transformative potential of human ingenuity and the enduring allure of the cosmos. Sunlight takes 8 minutes to reach Earth. Sunlight's 8-minute journey to Earth is a testament to the vastness of space and the incredible speed of light. We often take for granted the warmth and light that bathes our planet, but the story behind its arrival is fascinating. The Sun, a massive ball of burning gas located approximately 93 million miles away, constantly emits energy in the form of electromagnetic radiation, including visible light. This light, composed of photons, embarks on its cosmic voyage towards us at the mind-boggling speed of 186,282 miles per second. Even at this tremendous pace, the journey isn't instantaneous. Imagine a photon leaving the sun's surface. It's a chaotic environment with constant eruptions and magnetic storms. The photon initially struggles to escape, bouncing around within the dense solar interior for possibly millions of years before finally breaking free. Once released into the vacuum of space, the photon travels in a straight line, unimpeded by any significant obstacles. It hurtles through the emptiness, a silent messenger carrying energy and light. As the photon speeds towards Earth, it passes by other celestial bodies like Mercury and Venus, reflecting off their surfaces and contributing to their illumination. The sunlight that reaches Earth isn't just direct light from the sun. It's also diffused light that has been scattered by particles in space and our own atmosphere. This scattering is what gives us the beautiful blue color of the sky. The 8-minute travel time also means we are always seeing the sun as it was 8 minutes ago. If the sun were to suddenly disappear, we wouldn't know about it for another 8 minutes. This lag highlights the concept of time and distance in space, where events are not always perceived instantaneously. This has significant implications for astronomy and our understanding of the universe. Furthermore, the fact that sunlight takes 8 minutes to reach us underscores the importance of the sun's stability. Any fluctuations in solar output would not be immediately felt on Earth. This buffer period provides a degree of protection against sudden and drastic changes in the sun's energy emission, although significant solar flares can still have noticeable effects on our planet. The light that finally reaches our eyes has undergone an incredible transformation. It started as raw energy deep within the sun's core and traveled across vast distances to deliver warmth, enable photosynthesis, and illuminate our world. The sun's rays are vital for life on Earth, and the knowledge that these rays embarked on their journey just 8 minutes prior to reaching us allows for a profound appreciation of the universe's immense scale and the delicate balance that sustains us. It is a continuous process, with photons constantly being emitted, traveling through space and reaching our planet, ensuring the continuous cycle of light and energy that sustains life as we know it. The next time you feel the sun's warmth on your face, remember the incredible journey those photons have taken. The asteroid belt is between Mars and Jupiter. The asteroid belt, a region teeming with rocky debris, resides in the vast expanse between the orbits of Mars and Jupiter. Picture a cosmic junkyard, but instead of discarded cars and appliances, it is filled with remnants from the solar system's early formation. These remnants, known as asteroids, vary dramatically in size, shape, and composition. Some are colossal, dwarfing terrestrial mountains, while others are merely pebbles, barely noticeable amidst the celestial backdrop. The largest inhabitant of the asteroid belt series is so massive that it has been classified as a dwarf planet, holding the distinction of being the only dwarf planet within the inner solar system. This round, icy body makes up a significant portion of the belt's total mass. The asteroid belt's formation is intrinsically linked to the colossal presence of Jupiter. The immense gravitational influence of this gas giant disrupted the accretion process in the region, preventing the smaller bodies from coalescing into a larger planet. Instead, they were left to orbit the sun as a collection of fragmented material, forever caught in a gravitational tug-of-war. Despite depictions in science fiction films, the asteroid belt is not a densely packed field of rocks. The asteroids are spread out over a vast area, with substantial distances separating them. A spacecraft traversing the asteroid belt would likely not encounter any asteroids at all, highlighting the spacious nature of this region. The composition of asteroids offers valuable clues about the early solar system. Some are primarily composed of rock, while others are rich in metals, such as iron and nickel. Still others contain significant amounts of water ice, hinting at the presence of water in the inner solar system's formative years. These compositional differences suggest that the asteroids originated from various regions of the protoplanetary disk, the swirling cloud of gas and dust from which the planets formed. Scientists meticulously study the asteroid belt, not only to understand the solar system's history, but also to assess potential threats. A small percentage of asteroids, known as near-Earth asteroids, have orbits that bring them relatively close to our planet. While the vast majority pose no immediate danger, scientists carefully monitor their trajectories to identify any that might pose a future collision risk. This vigilance is crucial for planetary defense, as even a relatively small asteroid impact could have devastating consequences. Furthermore, the asteroid belt is also a potential source of valuable resources. The metallic asteroids in particular are rich in valuable metals that could be mined in the future. Asteroid mining, while still in its early stages of development, holds the promise of providing resources for space exploration and potentially even supplementing terrestrial supplies. In essence, the asteroid belt serves as a time capsule, preserving remnants of the early solar system and offering insights into the processes that shaped our planetary neighborhood. Its study continues to unveil fascinating details about the formation and evolution of our solar system and may even hold the key to future resource utilization in space. The ISS has been continuously inhabited since 2000. The International Space Station, or ISS, stands as a testament to human collaboration and ingenuity, a beacon of scientific exploration orbiting our planet. One particularly remarkable aspect of this orbital laboratory is the fact that it has been continuously inhabited since the year 2000. This unbroken chain of human presence in space represents an unprecedented achievement in the history of space exploration, showcasing the dedication and meticulous planning required to sustain life beyond Earth for extended periods. Imagine, for over 2 decades, there hasn't been a single moment when the ISS has been devoid of human occupants. Astronauts and cosmonauts, representing a multitude of nations, have cycled through the station, conducting experiments, maintaining vital systems, and pushing the boundaries of our understanding of the universe and ourselves. Consider the sheer logistics involved in maintaining this continuous habitation. Every resource, from food and water to oxygen and scientific equipment, must be carefully planned, packaged, and transported to the ISS. Resupply missions, utilizing spacecraft from various space agencies, are crucial for keeping the station operational and its inhabitants alive. These missions are not simply deliveries, they are a lifeline, ensuring the continued viability of the ISS as a research platform. The process is complex, involving precise calculations to account for the station's orbital path and the timing of launch windows. Failure to deliver essential supplies could have dire consequences for the crew and the ongoing scientific research. The environment of the ISS itself presents unique challenges to continuous habitation. Living in microgravity affects the human body in numerous ways, from bone density loss and muscle atrophy to changes in fluid distribution and vision. Astronauts must engage in rigorous exercise routines to mitigate these effects and maintain their physical health. Moreover, the station is exposed to harsh radiation from the sun and cosmic rays, requiring shielding and protective measures to minimize risks to the crew. The psychological impact of prolonged isolation and confinement in a closed environment is also a significant consideration. Astronauts undergo extensive training to cope with the mental and emotional demands of living in space, and regular communication with family and friends on Earth is vital for maintaining morale. The continuous human presence on the ISS has enabled a vast range of scientific research that would be impossible to conduct on Earth. Scientists are able to study the effects of microgravity on biological systems, develop new materials and technologies, and observe Earth from a unique vantage point. Research conducted on the ISS has led to advancements in fields such as medicine, materials, science, and climate science, with potential benefits for people around the world. Furthermore, the ISS serves as a crucial testing ground for technologies and procedures that will be essential for future long-duration space missions, such as those planned for the Moon and Mars. The lessons learned from sustaining human life in space for over 2 decades are invaluable for paving the way for humanity's expansion beyond Earth. The continuous habitation of the ISS is not just a remarkable feat of engineering and logistics. It is a testament to our enduring spirit of exploration and our unwavering commitment to expanding the frontiers of human knowledge. The Milky Way and Andromeda will collide in 4.5 billion years. In the vast cosmic tapestry of the universe, a spectacular event is brewing, a celestial dance set to unfold over billions of years. Our own galaxy, the Milky Way, is destined for a head-on collision with its massive neighbor, the Andromeda Galaxy, approximately 4.5 billion years from now. This galactic merger is not an apocalyptic doomsday scenario, but rather a slow, drawn-out process of gravitational interaction and eventual coalescence, a cosmic ballet on an unimaginable scale. The immense distances between stars within each galaxy ensure that individual stellar collisions will be exceedingly rare. Instead, the two galaxies will gradually distort each other through gravitational forces, their elegant spiral structures warping and merging into a new, hybrid form. Imagine two colossal whirlpools of stars, gas, and dust slowly approaching each other. As they draw closer, gravity will begin to tug and pull at their outer edges, creating spectacular tidal streams of stars stretching across millions of light years. These streams will act as cosmic bridges, connecting the two galaxies long before their central cores actually collide. Over time, the gravitational forces will become more intense, causing the galaxies to lose their distinct spiral shapes. The once well-defined arms of stars will become tangled and stretched, forming chaotic patterns in space. The supermassive black holes residing at the centers of each galaxy will also begin to feel each other's presence. These behemoths, millions or even billions of times more massive than our Sun, will spiral inward towards each other, engaging in a gravitational tango that will ultimately lead to their own merger. This union will unleash tremendous amounts of energy in the form of gravitational waves, ripples in the fabric of spacetime. The eventual result of this galactic merger will be a new, larger galaxy, often referred to as Milkomeda or Milkdromeda. This elliptical galaxy will likely lack the graceful spiral arms of its progenitors, possessing instead a more diffuse and rounded shape. The distribution of stars will be dramatically altered, with stellar populations from both galaxies intermixing throughout the newly formed structure. Our solar system, currently located in one of the Milky Way spiral arms, will likely be flung to a new location within the merged galaxy. While the exact trajectory is impossible to predict with certainty, the chances of our Sun colliding with another star during the merger are astronomically low. The most significant impact on our solar system will be the drastically altered night sky. The familiar constellations of the Milky Way will disappear, replaced by a dazzling display of billions of stars from both galaxies, creating a truly awe-inspiring spectacle. Even though 4.5 billion years is an unfathomable amount of time, the Andromeda galaxy is already visible to the naked eye as a faint, fuzzy patch of light in the night sky. It is constantly approaching us at a speed of about 110 kilometers per second, or roughly 250,000 miles per hour. While this speed seems incredibly fast, the immense distance separating us from Andromeda means that the collision will still take billions of years to unfold. Scientists have been able to predict this collision by meticulously studying the motions of both galaxies, using sophisticated telescopes and computer simulations to model their future interactions. This galactic merger is not unique in the universe. In fact, it is a common occurrence, playing a significant role in the evolution of galaxies over cosmic time. By studying these mergers, astronomers can gain valuable insights into the formation and growth of galaxies, unraveling the mysteries of the universe and our place within it. This grand cosmic collision serves as a powerful reminder of the dynamic and ever-changing nature of the universe, a testament to the ongoing dance of gravity and the breathtaking beauty of celestial evolution. The Milky Way contains 100 to 400 billion stars. The Milky Way, our home galaxy, is a vast and awe-inspiring cosmic structure containing an estimated 100 to 400 billion stars. This staggering figure underscores the sheer scale of our galactic neighborhood. Imagine trying to count every grain of sand on a beach. That's the kind of challenge astronomers face when attempting to precisely quantify the number of stars within the Milky Way. The variance in the estimate stems from the difficulties in observing distant and obscured regions of the galaxy, as well as the challenge of distinguishing individual stars from dense clusters and nebulous clouds. Think about our own Sun. It's just one star among these billions, a relatively ordinary one at that. Each of these stars is a potential sun, perhaps with its own retinue of planets, moons, and asteroids. Some of these stars are much larger and brighter than our Sun. while others are far smaller and dimmer, red dwarfs that burn their fuel at a glacial pace. The immense diversity in stellar types contributes to the Milky Way's dazzling complexity. These stars are not uniformly distributed throughout the galaxy. They are concentrated in a central bulge, a flattened disk, and a surrounding halo. The disk, where our solar system resides, is characterized by swirling spiral arms, structures rich in gas, dust, and newly formed stars. These arms are like cosmic highways, facilitating the birth and evolution of stellar systems. The central bulge is a densely packed region dominated by older stars and a supermassive black hole called Sagittarius A*. This behemoth has a mass millions of times greater than our Sun and exerts a powerful gravitational influence on the surrounding stars and gas. The galactic halo is a more diffuse region, containing globular clusters, ancient groupings of stars that predate the galactic disk. Consider the distances involved. Light, traveling at approximately 300,000 kilometers per second, takes years to traverse even the shortest interstellar distances. The Milky Way itself is estimated to be 100,000 to 180,000 light-years in diameter. This means that light from the farthest stars in our galaxy takes up to 180,000 years to reach us. When we gaze at the night sky, we are seeing stars as they were tens, hundreds, or even thousands of years ago. The light from some distant stars began its journey long before the pyramids were built. Moreover, the number of stars in the Milky Way is not a static figure. New stars are constantly being born from collapsing clouds of gas and dust, while older stars eventually exhaust their fuel and meet their end as white dwarfs, neutron stars, or black holes. This continuous cycle of stellar birth and death shapes the evolution of the Milky Way and enriches the galaxy with heavy elements, the building blocks of planets and life. The sheer number of stars in the Milky Way also has implications for the likelihood of finding life beyond Earth. With so many stars, the probability of at least some of them hosting habitable planets seems increasingly plausible. The search for extraterrestrial life, fueled by the vastness of our galaxy, continues to drive astronomical research and inspire our imaginations. This exploration emphasizes that the Milky Way, with its billions of stars, is not just a collection of celestial objects, but a dynamic and evolving ecosystem, a cosmic tapestry woven from light, gravity, and the raw materials of the universe. The Moon drifts away from Earth 1.5 inches per year. The Moon, our celestial companion, is not a static object forever locked in a fixed embrace with Earth. Instead, is engaged in a slow, almost imperceptible dance, one that sees it gradually drifting away from us at a rate of about 1.5 inches per year. While this may seem like an insignificant amount, over vast stretches of cosmic time, this lunar departure has profound implications for both the Moon and our planet. Imagine stacking approximately 4 quarters end to end each year. That's the distance the Moon is increasing its separation from Earth. So what's causing this lunar farewell? The primary culprit is the process of tidal interaction. Earth's gravity exerts a powerful pull on the Moon, and conversely, the Moon's gravity also tugs on Earth, most visibly in the form of ocean tides. These tides aren't just surface phenomena. They create a bulge of water on the side of Earth, facing the Moon, and another on the opposite side. As Earth rotates faster than the Moon orbits, this tidal bulge is pulled slightly ahead of the Moon's position. The Moon's gravity then tugs on this bulge, which in turn exerts a forward pull on the Moon, accelerating it slightly in its orbit. This acceleration causes the Moon to spiral outwards, gradually increasing its distance from Earth. But the story doesn't end there. This tidal interaction is a two-way street. While the Moon gains energy and moves further away, Earth loses energy in the process. This loss of energy manifests as a slowing down of Earth's rotation. Think of it as a cosmic seesaw. The Moon gains altitude, while Earth loses rotational speed. Over millions of years, this has resulted in Earth days becoming longer. In the distant past, a day on Earth was significantly shorter, perhaps only a few hours long. The length of a day has been steadily increasing due to the Moon's influence. The implications of the Moon's departure extend beyond just longer days. It also affects Earth's climate and stability. The moon plays a crucial role in stabilizing Earth's axial tilt, which is the angle at which Earth is tilted on its axis of rotation. This tilt is responsible for the seasons we experience. Without the moon's stabilizing influence, Earth's axial tilt could wobble significantly, leading to dramatic and unpredictable climate changes. Furthermore, a closer moon in the past meant more dramatic tides. Coastal regions would have experienced much larger tidal ranges, potentially reshaping coastlines and affecting marine life. The gradual retreat of the moon has allowed for the stabilization of these tidal forces, creating the more predictable and less extreme tidal patterns we observe today. It's important to remember that this is an incredibly slow process, happening over millions and billions of years. So there is no need to worry about the moon suddenly disappearing from our night sky. However, the fact that our moon is slowly drifting away provides us with a fascinating glimpse into the dynamic and ever-changing nature of our solar system, and the intricate interplay of gravitational forces that shape the destinies of planets and moons alike. The slow dance between Earth and its moon is a testament to the enduring power of gravity and the constantly evolving relationship between celestial bodies. The sun energy comes from nuclear fusion. The sun, a colossal star dominating our solar system, radiates an immense amount of energy, a force that sustains life on Earth and dictates the dynamics of the planets. This energy doesn't originate from burning like a conventional fire, but from a much more powerful and intricate process called nuclear fusion. Deep within the sun's core, under unimaginable pressures and temperatures reaching 15 million degrees Celsius, hydrogen atoms are forced to collide and fuse together, transforming into helium atoms. This transformation might seem simple, but it releases an astonishing amount of energy, explained by Einstein's famous equation, E = mc squared. This equation reveals that a tiny amount of mass is converted into a tremendous amount of energy during the fusion process. To illustrate the scale, the sun converts about 600 million tons of hydrogen into helium every second, and in doing so, it converts about 4 million tons of matter into energy. The process primarily involves the proton-proton chain reaction. This multi-step process begins with two protons fusing to form deuterium, a heavier isotope of hydrogen. Deuterium then fuses with another proton to create helium-3. Finally, two helium-3 nuclei fuse to form helium-4, releasing two protons in the process. These newly released protons can then participate in further fusion reactions, sustaining the cycle. The energy released is in the form of gamma rays and neutrinos. Gamma rays, high-energy photons, embark on a long and arduous journey from the sun's core to its surface. This journey can take hundreds of thousands to millions of years. The photons are constantly absorbed and re-emitted by the dense plasma in the sun's interior, gradually losing energy and transforming into lower-energy photons, mostly visible light, which eventually escapes the sun's surface and floods our solar system. Neutrinos, on the other hand, are nearly massless particles that interact very weakly with matter. They escape the sun's core almost immediately, traveling at nearly the speed of light. Studying these solar neutrinos provides valuable insights into the nuclear reactions occurring in the sun's core, confirming our understanding of nuclear fusion. The sun's energy production is remarkably stable, a delicate balance between gravity, which tries to compress the sun, and the outward pressure generated by the nuclear fusion reactions. This balance, known as hydrostatic equilibrium, ensures that the sun shines steadily over billions of years. However, the sun is not an inexhaustible energy source. It has been fusing hydrogen for about 4.5 billion years, and is estimated to continue for another 5 billion years. Eventually, the sun will exhaust the hydrogen fuel in its core, leading to significant changes in its structure and energy output, ultimately transforming it into a red giant star, before eventually becoming a white dwarf. Understanding the sun's energy source through nuclear fusion is critical for comprehending not only our solar system, but also the evolution and behavior of stars throughout the universe. It highlights the power of nuclear processes and their vital role in shaping the cosmos. The sun makes up 99.86% of the solar system mass. Imagine our solar system as a grand cosmic ballet, with a single brilliant star as the prima ballerina and all the planets, asteroids, and comets as the supporting cast. This leading lady, of course, is our Sun, and her dominance in the performance is utterly breathtaking. The Sun constitutes a staggering 99.86% of the entire solar system's mass. To truly grasp the magnitude of this figure, let's break it down and explore its implications. Think of it this way. If you were to gather all the planets, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, and then combine all the asteroids, comets, moons, and dust in our solar neighborhood, the combined mass of all that celestial debris would only account for a mere 0.14% of the total mass. The Sun's colossal weight dwarfs everything else into insignificance. It's like trying to compare the weight of an elephant to that of a feather. The sheer difference in scale is almost incomprehensible. This immense mass is primarily due to the Sun's sheer size and density. It's a giant ball of hot plasma, primarily hydrogen and helium, undergoing constant nuclear fusion in its core. This fusion process, where hydrogen atoms are forced together under immense pressure and temperature to form helium, releases an incredible amount of energy in the form of light and heat, which sustains life on Earth. The immense pressure needed for this fusion to occur contributes greatly to the Sun's overall density. The Sun's gravitational influence is directly proportional to its mass. This means that it's the Sun's gravity that dictates the orbits of all the other objects in our solar system. Planets revolve around the Sun in elliptical paths, held captive by its powerful gravitational pull. Without the Sun's immense mass, these planets would simply drift off into interstellar space, scattering like billiard balls after a powerful break. The Sun's mass is what binds our solar system together, creating a cohesive and dynamic system. Interestingly, the Sun's composition is not uniform throughout. While it's primarily made of hydrogen and helium, it also contains trace amounts of heavier elements like oxygen, carbon, nitrogen, silicon, magnesium, neon, iron, and sulfur. These heavier elements, though present in small quantities, play a crucial role in the Sun's energy production and internal structure. Scientists are constantly studying the Sun's composition to gain a better understanding of its formation, evolution, and ultimate fate. The study of these heavier elements is vital in understanding the formation process of stars. Furthermore, understanding the Sun's mass is crucial for understanding its lifespan. The more massive a star, the shorter its lifespan. While the Sun is massive compared to other objects in our solar system, it is considered an average-sized star. This means it has a relatively long lifespan, estimated to be around 10 billion years. It has already burned through roughly half of its hydrogen fuel, and is currently in its stable middle age. The Sun's mass dictates the speed at which it consumes its fuel. In conclusion, the fact that the Sun accounts for 99.86% of the solar system's mass underscores its absolute dominance and profound influence on our corner of the cosmos. It is the engine that drives our solar system, the source of life-giving energy, and the gravitational anchor that holds everything together. Its immense mass is not just a number, it's a fundamental property that shapes the very nature of our solar system and our existence within it. The universe is 13.8 billion years old. Imagine stepping into a time machine, setting the dial not for tomorrow or next year, but for 13.8 billion years ago. That's how long ago the universe as we know it burst into existence. This astonishing age isn't just a number. It's a testament to the vast, almost incomprehensible scale of cosmic history. How do scientists even begin to fathom such a mind-boggling time frame? It all started with the Big Bang, the event that birthed space, time, and everything within them. Think of it as the ultimate cosmic firework, an explosion of unimaginable energy that continues to echo through the universe as it expands. Determining the age of the universe is no easy task. It's a puzzle that requires piecing together clues from various sources. One of the most crucial clues comes from the cosmic microwave background, often referred to as the afterglow of the Big Bang. This faint radiation permeates the entire universe, a relic of the incredibly hot and dense conditions that existed in the early moments of its existence. By studying the patterns and temperature fluctuations in the cosmic microwave background, scientists can infer the age and composition of the early universe. Another key piece of the puzzle lies in observing the expansion rate of the universe. Galaxies are constantly moving away from each other, a phenomenon known as Hubble's law. By measuring the speed at which these galaxies are receding, astronomers can extrapolate backward in time to estimate when the expansion began, essentially pinpointing the moment of the Big Bang. This process is akin to watching a balloon inflate and calculating when it was initially deflated. However, the universe's age isn't just a scientific fact. It's a philosophical and existential one. It forces us to confront our place within the grand cosmic narrative. Humans, with our relatively short lifespans, are but fleeting moments in the vast expanse of cosmic time. Civilizations rise and fall, stars are born and die, and galaxies collide over timescales that dwarf human history. It's humbling to realize that the universe existed for billions of years before our planet even formed. The age of the universe also challenges our understanding of the very fabric of reality. During the first few moments after the Big Bang, the universe was in a state of extreme energy and density, a realm where the laws of physics as we know them break down. Studying the early universe requires delving into the realms of quantum mechanics and general relativity, pushing the boundaries of our scientific knowledge. Moreover, the age of the universe provides a framework for understanding the evolution of galaxies, stars, and planets. It explains why the oldest stars are found in globular clusters, ancient collections of stars that formed in the early universe. It also explains why heavier elements, such as iron and gold, are relatively rare, as they were forged in the cores of dying stars over billions of years. Every element we encounter, every star we observe, every galaxy we photograph, is a testament to the immense amount of time that has passed since the Big Bang. In essence, the fact that the universe is 13.8 billion years old is not just a scientific data point. It's a gateway to understanding the grand scale of cosmic history, our place within it, and the fundamental laws that govern the universe. It's a reminder that we are part of something far grander and more ancient than ourselves, a story that continues to unfold with each passing moment. Titan has lakes of liquid methane and ethane. Titan, the largest moon of Saturn, is an extraordinarily unique celestial body in our solar system, and it holds a special distinction. It's the only moon known to possess a dense atmosphere and stable bodies of surface liquid. However, unlike Earth, where water dominates, Titan boasts lakes and seas composed of liquid methane and ethane. This captivating aspect of Titan makes it a subject of intense scientific curiosity. Imagine a world where rain showers not water but methane, and where rivers of ethane carve pathways through icy terrains, eventually emptying into sprawling hydrocarbon lakes. These lakes, varying greatly in size, are predominantly found near Titan's polar regions. One of the largest, Kraken Mare, is comparable in size to the Caspian Sea on Earth. Its vast expanse holds a significant portion of Titan's liquid reserves, influencing the moon's overall climate and weather patterns. The composition of these liquid bodies isn't solely methane and ethane. Scientists believe they contain dissolved nitrogen, adding to the chemical complexity of Titan's hydrological cycle. The presence of these liquid hydrocarbon lakes speaks volumes about Titan's frigid environment, with surface temperatures plummeting to around minus 179 degrees Celsius. Methane and ethane, which are gases on Earth, exist in liquid form. This temperature also dictates the moon's geology. Instead of silicate rocks, Titan's surface is primarily composed of water ice, which is as hard as rock at these extremely low temperatures. This icy bedrock forms the landscape through which methane and ethane rivers flow. The dynamics of Titan's lakes are also fascinating. While some appear relatively still, others exhibit evidence of wave activity, suggesting the presence of winds on Titan. The exact mechanisms driving these winds and waves are still under investigation, but they are thought to be related to the seasonal changes in sunlight and temperature that Titan experiences over Saturn's long orbital period. Just as Earth's lakes and oceans play a crucial role in regulating our planet's climate, Titan's hydrocarbon lakes significantly impact its atmospheric processes. The study of Titan's lakes and their composition is crucial for understanding the Moon's potential for prebiotic chemistry. Although life as we know it on Earth requires liquid water, scientists speculate that life based on different chemistries could potentially exist in Titan's hydrocarbon environment. The presence of organic molecules, combined with liquid methane and ethane, could provide a unique setting for complex chemical reactions to occur. While there is no direct evidence of life on Titan, the existence of these lakes fuels scientific investigations into the possibility of alternative forms of life beyond Earth. Future missions to Titan, equipped with advanced instruments, are expected to further explore the composition, dynamics, and potential habitability of these extraordinary hydrocarbon lakes. These future explorations may offer insight into the conditions that may give rise to life, even if life looks drastically different from our own. Uranus rotates on its side. Uranus, the seventh planet from the Sun, presents a peculiar characteristic that sets it apart from the other planets in our solar system: its rotation on its side. Imagine the Earth spinning like a top, upright and dignified. Now picture Uranus, tilted over so dramatically that it spins like a rolling ball. This unusual orientation means its axis of rotation is inclined at a staggering 98 degrees relative to its orbit around the Sun. This near-sideways spin has fascinating implications for the planet's seasons and overall appearance. Unlike Earth, where the equator receives the most direct sunlight, Uranus experiences periods where either its north pole or its south pole is pointed almost directly at the Sun. This leads to extreme seasonal variations. For nearly a quarter of Uranus's 84-year orbit, one pole faces the Sun continuously, experiencing a 42-year-long summer. Meanwhile, the opposite pole remains in darkness for an equally long winter. As Uranus travels around the Sun, the equator experiences sunrise and sunset, but the intensity of sunlight is significantly weaker compared to the poles during their respective summers. This bizarre seasonal cycle creates drastic temperature differences between the sunlit and shadowed hemispheres. Scientists are still trying to fully understand how these extreme seasonal changes affect Uranus's atmosphere and weather patterns. Adding to the intrigue, Uranus's magnetic field is also strangely tilted and offset. It's not aligned with the planet's rotational axis like most other planets. Instead, it's tilted by about 60 degrees and displaced from the center of the planet by a substantial fraction of Uranus's radius. This creates a lopsided magnetosphere, the region of space dominated by the planet's magnetic field. The magnetosphere interacts with the solar wind, the stream of charged particles emanating from the Sun, in a complex and dynamic way. The unusual shape and orientation of Uranus's magnetosphere make it a unique and fascinating subject of study for space physicists. The reason for Uranus's extreme tilt remains a mystery, although the prevailing theory suggests that it was struck by a massive object, perhaps a protoplanet, early in its history. Such a collision could have knocked Uranus onto its side, disrupting its original rotation and causing the unusual features we observe today. Alternatively, it is hypothesized that multiple smaller collisions could have gradually tilted the planet over time. Another possibility involves gravitational interactions with other giant planets during the solar system's formative years. These interactions could have destabilized Uranus's orbit and tilted its axis of rotation. While the exact cause of Uranus's tilt is still debated, the evidence points to a dramatic and violent event in the planet's past. This event not only altered Uranus's rotation, but likely also affected its internal structure, atmospheric composition, and the formation of its ring system and moons. Understanding the origins of Uranus's unusual tilt is crucial for unraveling the mysteries of the solar system's evolution and the processes that shape the planets we see today. Further exploration and research, including future missions to Uranus, will undoubtedly shed more light on this fascinating and enigmatic planet. Ui Scuti is the largest known star. Ui Scuti reigns supreme as the largest known star in the observable universe, a celestial behemoth dwarfing our own Sun to an almost unimaginable degree. This red hypergiant resides approximately 9,500 light-years away from Earth, nestled within the constellation Scutum, a region of the Milky Way galaxy teeming with stars. The sheer scale of Ui Scuti is what truly captures the imagination. Its radius is estimated to be around 1,700 times that of the Sun. To put this into perspective, if Ui Scuti were placed at the center of our solar system, its surface would extend past the orbit of Jupiter, potentially even reaching Saturn. This means that it would take light, traveling at its immense speed, roughly 6 hours, to circumnavigate the star, a journey that would take a mere 14.5 seconds around our Sun. The implications of such a vast size are staggering. Ui Scuti is so large that it could theoretically contain over 5 billion suns within its volume. However, despite its enormous dimensions, Ui Scuti is not the most massive star known. Its density is incredibly low, far less than the density of our Sun. This is typical of red hypergiants, stars nearing the end of their lives and undergoing rapid mass loss. Ui Scuti is shedding material into space at an alarming rate, forming a vast circumstellar envelope around the star. This envelope, composed of gas and dust ejected from the star's outer layers, makes it difficult to precisely determine its size and luminosity. Ui Scuti's classification as a red hypergiant is significant because it indicates its evolutionary stage. These stars are extremely luminous and unstable, existing for a relatively short period of time compared to smaller, more stable stars like our Sun. They are nearing the end of their nuclear fusion processes, having exhausted much of the hydrogen fuel in their cores. As a result, they have expanded dramatically, cooled, and become redder in color. Ui Scuti is expected to eventually end its life in a spectacular supernova explosion, leaving behind either a neutron star or a black hole. The discovery and study of Ui Scuti have been crucial in expanding our understanding of stellar evolution and the life cycles of stars. Astronomers continue to refine measurements of its size, luminosity, and mass loss rate, seeking to gain further insights into the processes that govern the behavior of these extreme objects. While other stars have been proposed as potential contenders for the title of largest star, Ui Scuti remains the undisputed champion based on current data. Its sheer size challenges our perceptions of scale and reminds us of the vastness and diversity of the cosmos. The existence of Ui Scuti serves as a humbling reminder of our place in the universe. A tiny speck of dust orbiting a relatively small star in a galaxy filled with wonders beyond our comprehension. Further research and observations will undoubtedly reveal even more fascinating details about this extraordinary star and its ultimate fate, solidifying its place in the annals of astronomical discovery. Venus' day is longer than its year. Venus, often called Earth's sister planet due to its similar size and rocky composition, harbors a fascinating anomaly in its orbital mechanics. A Venusian day is longer than a Venusian year. This seemingly paradoxical situation arises from the planet's incredibly slow rotation and its relatively quick orbit around the Sun. Let's delve into the details of this captivating space fact. A day on Venus, which is the time it takes for the planet to complete one rotation on its axis, lasts approximately 243 Earth days. In stark contrast, a year on Venus, defined as the time it takes for the planet to complete one orbit around the Sun, is only about 225 Earth days. This means that the time it takes for Venus to spin once is longer than the time it takes to circle the Sun. This is extremely unusual in our solar system, where most planets have days much shorter than their years. The reason for Venus's sluggish rotation is still a matter of scientific investigation, but several theories attempt to explain this phenomenon. One leading hypothesis suggests that early in its history, Venus may have experienced a massive collision with another celestial object. This impact could have dramatically altered the planet's original spin, slowing it down to the incredibly slow pace we observe today. Another possibility involves the interaction between Venus's dense atmosphere and its solid surface. The intense winds in the Venusian atmosphere might exert a drag on the planet's rotation, gradually slowing it down over billions of years. The exact mechanism responsible is likely a combination of factors, making it a complex and ongoing area of research. Adding to the peculiarity, Venus also rotates in a retrograde direction, meaning it spins clockwise as seen from above its north pole, opposite to the rotation of most other planets in our solar system, including Earth. This retrograde rotation further distinguishes Venus from its planetary neighbors. The combination of its slow retrograde rotation and its relatively fast orbit results in an unusual experience for a hypothetical observer on the Venusian surface. Due to the planet's slow rotation, the sun rises in the west and sets in the east, the opposite of what we observe on Earth. Furthermore, because a day is longer than a year, the sun would rise and set only twice during a Venusian year. Imagine witnessing a sunrise only to see another one before you complete a full orbit around the sun. Another consequence of Venus's slow rotation is the effect it has on its magnetic field. Unlike Earth, which has a strong magnetic field generated by the movement of molten iron in its core, Venus lacks a global magnetic field. This is likely due to the planet's slow rotation, which is not sufficient to drive the dynamo effect necessary for generating a magnetic field. Without a magnetic field to deflect charged particles from the sun, Venus's atmosphere is directly exposed to the solar wind, which may have contributed to the loss of water on the planet over billions of years. The absence of a magnetic field also makes Venus's atmosphere more vulnerable to being stripped away by the solar wind, further altering its climate over time. In conclusion, the fact that a day on Venus is longer than its year is not just a quirky detail. It's a key piece of the puzzle in understanding the planet's unique history, its atmospheric dynamics, and its overall evolution. The planet's slow retrograde rotation, potentially caused by ancient collisions or atmospheric drag, leads to bizarre phenomena such as sunrises in the west and the absence of a global magnetic field. Venus serves as a fascinating case study for planetary scientists seeking to understand the diverse range of conditions that can exist in our solar system and beyond. Venus is the hottest planet in the solar system. Venus reigns supreme as the hottest planet in our solar system, a scorching world where surface temperatures soar to a staggering 900 degrees Fahrenheit. This is hot enough to melt lead, a detail that vividly illustrates the extreme conditions on this seemingly similar yet drastically different neighbor to Earth. What makes Venus so incredibly hot? It's not simply its proximity to the sun, although that certainly plays a role. The key culprit is its extraordinarily dense atmosphere, a thick blanket composed primarily of carbon dioxide. This carbon dioxide atmosphere traps heat through a runaway greenhouse effect. Sunlight penetrates the atmosphere and warms the surface of Venus. However, the heat radiating back from the surface cannot escape back into space because it is absorbed by the carbon dioxide. This trapped heat continues to build up, leading to the planet's incredibly high temperatures. Think of it like a car parked in the sun with the windows rolled up. The sun's rays enter, but the heat can't escape, causing the interior temperature to skyrocket. Venus is the ultimate example of this phenomenon on a planetary scale. Adding to the hostile environment are the clouds of Venus, which are not made of water vapor like on Earth, but instead are composed of sulfuric acid. These clouds completely shroud the planet, making it impossible to see the surface from space in visible light. This perpetual cloud cover also contributes to the greenhouse effect, reflecting some sunlight back into the atmosphere and further contributing to the heat. Furthermore, the atmospheric pressure on Venus is immense, about 90 times greater than on Earth. This is equivalent to the pressure one would experience a kilometer deep in the ocean on Earth. A human on the surface of Venus would be crushed instantly. While Venus and Earth are often referred to as sister planets due to their similar size, mass, and density, the conditions on their surfaces are vastly different. Earth is a vibrant, life-sustaining world, while Venus is an inferno. This difference highlights the delicate balance required for a planet to be habitable. Interestingly, there is evidence to suggest that Venus may have once been a much more hospitable place. Scientists believe that early Venus may have had oceans and a more temperate climate. However, a runaway greenhouse effect, triggered by volcanic activity or other factors, led to the planet's current state. Studying Venus provides valuable insights into the potential dangers of unchecked greenhouse gas emissions and the importance of maintaining a stable climate on Earth. Despite the harsh conditions, Venus continues to fascinate scientists. Space probes have been sent to Venus to study its atmosphere, surface, and geology. These missions have provided valuable data, helping us to understand the planet's evolution and the processes that have shaped it into the hottest planet in the solar system. Future missions are planned to further explore Venus, seeking to unravel its mysteries and potentially uncover more about its past and the possibility of past life. The extreme heat of Venus serves as a stark reminder of the power of planetary processes and the unique characteristics that make each planet in our solar system so distinct. Voyager 1 is the farthest human-made object. Voyager 1, a testament to human ingenuity and our relentless pursuit of understanding the cosmos, holds the distinguished title of being the farthest human-made object from Earth. Launched on September 5, 1977, this intrepid spacecraft was initially tasked with exploring the outer planets of our solar system, specifically Jupiter and Saturn. However, Voyager 1 exceeded its primary mission parameters and embarked on an unprecedented journey into the vast unknown, venturing into interstellar space. This achievement marks a pivotal moment in human history, signifying our ability to transcend the boundaries of our solar system and reach for the stars. The sheer distance Voyager 1 has traversed is staggering. As of 2023, it is located over 14 billion miles, or 22.5 billion kilometers from Earth. To put this into perspective, sunlight, which travels at the speed of light, takes approximately 20 hours to reach Voyager 1. This immense distance makes communication with the spacecraft a slow and deliberate process. Signals sent from Earth take nearly a full day to reach Voyager 1, and the return signals take an equal amount of time. Despite this communication delay, NASA engineers continue to monitor the spacecraft's health and receive valuable data from its instruments. One of the most remarkable aspects of Voyager 1 is its longevity. Designed to function for only a few years, the spacecraft has defied expectations and continued to operate for over 4 decades. This incredible feat is a testament to the robustness of its design and the dedication of the engineers who built and maintain it. Voyager 1 is powered by a radioisotope thermoelectric generator which converts the heat generated by the decay of plutonium-238 into electricity. This power source has gradually diminished over time, requiring engineers to carefully manage the spacecraft's resources and prioritize the operation of essential instruments. As Voyager 1 journeys through interstellar space, it is providing scientists with invaluable data about this largely unexplored region. The spacecraft is equipped with a suite of instruments that measure magnetic fields, plasma waves, and cosmic rays. These measurements are helping scientists to understand the properties of the interstellar medium, the tenuous gas and dust that exist between stars. Voyager 1's observations have revealed that the interstellar medium is a complex and dynamic environment, influenced by the activity of nearby stars and the galaxy's magnetic field. Perhaps one of the most iconic features of Voyager 1 is the Golden Record, a phonograph record containing sounds and images selected to portray the diversity of life and culture on Earth. The record includes greetings in 55 languages, a selection of music from various cultures and eras, and sounds of nature, such as the sound of rain, wind, and animals. The Golden Record is intended as a message to any extraterrestrial civilization that may encounter Voyager 1 in the distant future. It is a testament to humanity's hopes and dreams, and a symbol of our desire to connect with other intelligent life in the universe. Voyager 1's journey is expected to continue for many more years, albeit with diminishing power and limited functionality. Eventually, the spacecraft will fall silent, but its legacy will endure. Voyager 1 will forever be remembered as the first human-made object to venture into interstellar space, a pioneering ambassador of humanity to the cosmos. Its discoveries have expanded our understanding of the solar system and the interstellar medium, and its golden record carries a message of hope and goodwill to the stars. Voyager 1 serves as a powerful reminder of the boundless curiosity and ingenuity that drive human exploration. Yuri Gagarin was the first human in space. Yuri Gagarin's pioneering flight as the first human in space is a landmark achievement etched in the annals of space exploration. On April 12, 1961, aboard the Vostok 1 spacecraft, Gagarin embarked on a journey that lasted a mere 108 minutes, yet forever altered humanity's perception of its potential. His voyage wasn't just a personal triumph. It was a monumental victory for the Soviet Union, a beacon of its technological prowess during the heated Cold War era. The Vostok 1 spacecraft was a relatively simple machine by modern standards, consisting of a spherical descent module, where Gagarin was housed, and an equipment module containing engines and life support systems. Before the flight, the risks were substantial, and no one could guarantee Gagarin's safe return. Contingency plans were made, including a coded message pre-written for TASS, the Soviet news agency, which had both a success and failure announcement prepared. Gagarin was selected from a pool of 20 Soviet Air Force pilots for his exceptional physical condition, his ability to handle stress, and his charismatic personality. Standing at a modest 5 feet 2 inches, his height was actually an advantage, allowing him to fit more comfortably in the cramped Vostok capsule. Before the launch, Gagarin penned a heartfelt letter to his wife, Valentina, expressing his love and preparing her for the possibility that he might not return. This letter was only delivered to her 7 years later, after his tragic death. The launch from Baikonur Cosmodrome, now in Kazakhstan, was shrouded in secrecy. The world only learned of the mission's success after Gagarin had already orbited the Earth once. As the Vostok 1 soared into space, Gagarin famously uttered the phrase, "Poyekali," meaning, "let's go," a phrase that has since become synonymous with the dawn of the space age. During the flight, Gagarin experienced weightlessness and witnessed the curvature of the Earth from space. He reported his observations back to ground control, providing valuable data about the human experience in space. There were some malfunctions during the flight. For example, the spacecraft's orientation system malfunctioned, forcing the automatic system to use a backup solar sensor. The Vostok 1 was not designed for a soft landing. Gagarin ejected from the capsule at an altitude of about 7 kilometers and descended via parachute. This detail was initially kept secret by the Soviet Union, as the Fédération Aéronautique Internationale, the world governing body for air sports, stipulated that for a spaceflight to be officially recognized, the pilot had to land with the spacecraft. Gagarin's return to Earth was met with unparalleled celebration. He was hailed as a global hero, paraded through the streets of Moscow, and received accolades from leaders around the world. His image graced newspapers and magazines, and he became an instant symbol of human courage and technological achievement. Gagarin's flight opened the door for further human spaceflight and inspired generations to reach for the stars. Tragically, Yuri Gagarin died in a plane crash on March 27, 1968, during a routine training flight. His death was a devastating loss for the Soviet Union and the world. However, his legacy as the first human in space endures, a constant reminder of the boundless potential of human exploration and the bravery of those who dare to venture into the unknown.